this chapter of current electricity, it starts off with basic current parameters like density, drift speed, relaxation time, resistivity, resistance, EMF, all these things. Then slowly we move on from those to circuit problems, where you talk about batteries in combination, resistors in some combination, Wheatstone's bridge, and the power. So that is the basic flow of the chapter. If you remember little bit from your 10th standard, I hope you, probably, I don't know, maybe it has been a while. This is a much better extension of that chapter which you might have studied back in 10th grade. All right. So, okay, so this introduction part is just about telling you how current electricity is there everywhere. I mean, they talk about natural situations like lightning, as well as, a artificial man-made situation like a torch. So if you talk about your fans, your AC, your light, your torch, your computer, your mobile, all of them work on the principle of current electricity, and naturally occurring phenomena are like lightning. So when lightning occurs, current, basically flow of charges, happens from the clouds to the earth. So that is naturally occurring current. And if you ever wondered what a current is like a river, that's what they say. But a river which is, instead of carrying water, it is carrying charges. So a river which is like carrying charges, is that phenomena is being called as the current. Now we know that river will flow through a path. Same way the current will also flow through a path which is a conducting path, or else we wouldn't be able to survive or live. Just imagine somebody turns on the light, but instead of the current going inside the bulb, it flows through our body. It doesn't, because there is air, there is some insulation, rubber, wood, so many non-conducting materials are there, so which stops the flow of current, and it only allows the current in a certain path, which is the wire, which is a conductor. So that is what the basic introduction is. That's not so great or important. So just to build up the mood, like warming up, just like you guys warm up the chat box by putting those fire emojis. Hello, KV Thamis. Hi, Scientists of India. Welcome, welcome. Hi, Prasant. Yep. Now, the main things start from here, which is basically the electric current. Imagine a small area which is held normal to the flow. Both the positive and negative charges may flow forward, backward. In some intervals, some charges move this way, some charges move that way. And you might see that the total charge which flows is this much. Then the current is given by Q by T, which is defined to be the current across the area in the forward direction. If it turns out to be negative number, it implies the current is in the backward direction. Now the main things which you need to highlight over here is basically this, and is defined to be the current across the area in the forward direction. The net amount of charge flowing in the area forward direction in that time interval t is basically this much. Then this is the value. Okay, now I'll explain you what this means. Say for example, there is a positive charge. It goes like this, and it goes like that through some maybe cross-sectional area. Maybe through some cross-sectional area over here. So if that particular charge was, let's say, Q, and this moved in a time of t, then I will say that the current is flowing. I will say that the current is flowing in this direction, in the direction of the positive charge, and the value of the current is basically Q by T. I will say that the value of the current is the charge which flows in a unit time. Now just imagine the same cross section, but this time what happens is you have instead a negative charge. You have instead a negative charge, negative Q, which goes through that particular cross section in a time of t. Now if you ask me what is the current will still be Q by T, but it won't be here. Current is always assumed in the direction of the positive charges. Here negative charge goes this way. It is same as saying, if evil is going out of me, I am becoming better. If good is coming into me, I am becoming still better. I hope you understand both of them are creating the same kind of effect. If something good is coming into me, I'm becoming a good person. If evil is going out of me, you might say, sir, something is going out of you. But it's okay. It's the evil which is going out of me. Still, it is making me into a better person. So same way, if negative charges go here, is the same as saying the positivity is going on this side. Hence, the current will still be charged by time only, Q by T, but the direction will be here. Is that making absolute sense to all of you? Same way, now just imagine there is this cross section, and what happens is there are two positive charges which go like this through that particular cross section, okay, and there is one negative charge which basically goes through the cross section like this. You might be like, sir, this is combination of multiple charges. Now what is the current exactly? I'll tell you. These two charges going here will make the total charge going this side Q plus Q. This charge going here is same as saying a positive charge going this way. This is same as saying a positive charge going the left way. So actually the charge is not going right side, it is going left side. So I will put minus Q and this whole thing divided by time. Let's say there was one more charge over here which was going this way, then I would have put one more Q over here. So this will be the total current. So in this case, it will be 3Q minus Q, which is 2Q divided by T. Is that okay, my dear students? How this works? And then what if this is the scenario? Let's see if you guys can figure this out. But before that, the direction of the current in this scenario, was here. This was the direction of the current. Come on, my dear students, I want everyone to answer this. There are two positive charges which are going like this, and there are two negative charges which are basically going like this. There is one negative charge which is going like this. Okay, so tell me in this particular scenario, let's say there will be three charges. Now tell me in this particular scenario, what is the total current in the circuit? What is the total current in the circuit? So if you notice over here, three charges, positive charges are going towards the right hand side. So Q and Q and Q charges went to the right hand side. These negative charges going right is same as saying two positive charges went to the left. Two positive charges, it's same as saying two positive charges went towards the left. These two negative charges going towards the left is same as saying two positive charges went to the right. So won't these two end up cancelling out each other? Won't they end up cancelling out each other? That's it. The whole thing divided by time is the current. So these two cancelled. The positive charges went here. Hence the current in this scenario is towards the right hand side. So this is exactly what has been explained in this paragraph. So this formula might look simple, but you should know how to exactly apply it. Through these examples, I hope you have understood how this formula has to be applied or how you will actually use these things. Is this absolutely clear? Finally, yep. All right. Very good. Very good. Awesomeness. Awesomeness. Now, in the next part after this, okay, but before going ahead, they also tell you one more thing. Let's say I tell you that the current in this is 2 units, and I show the arrow mark like this. And there is another diagram where I show the current is like this, and the current I will say it is -3 units. What is the difference in these two? The difference in these two is, see, when I say the current is +2 and I show the arrow mark, means the positivity is going like this. The positivity is going like this. Or I can say alternatively, the negative charges are going like this. That is what it means. And the answer being positive tells whatever I have assumed is correct. If something is positive, that means whatever I assume is correct. But here it is negative, means whatever I assumed is wrong. So actually charges are not going here. So the charges positively are going here, or same as saying the negative charges are going this way. That is the meaning of negative value of the current. Don't get scared thinking, so current became negative, am I wrong? No, that's what they say. If the current is negative, then it just means the current is in the backward direction. So that is what they just say over here. So another important point over here, if it turns out to be negative number, it implies the current is in the opposite direction or the backward direction. That is what I have explained. Now the next part talks about the derivative of the charge with respect to time, and they have given one formula over here which is the same as dq by dt. And why they have given this is because current need not always be steady and it may increase and decrease. Sometimes more current goes, sometimes less current goes. Everybody might have turned on the fan and be like, oh sir, it is very hot, increase the fan, more current will come. The AC is not making me cold enough, make the AC speed fast. So you will make the AC stronger to blow more cold air. So it will take in more current. Or sometimes you are feeling very cold, you reduce the AC. So current can change with time. And when current changes with time, the charge which is going through it is also changing at different rates. Sometimes more charge, sometimes less charge, sometimes constant charge, sometimes again more charge, and even more charge, and again even less charge. So the rate at which the charge flows can change with time. So that is why you write it in the derivative form, which is the rate of flow of charge. And the unit of current also has been defined right over here. The unit of current is basically ampere, and ampere is nothing but how much charge flows per unit time. It is a coulomb of charge which goes in 1 second. So remember this, 1 ampere is nothing but 1 coulomb which goes in 1 second. Now this is a very informal definition. The formal definition comes in magnetism chapter. You will see why later on, but don't worry about it. Okay. Now if you ask me how big is an ampere, let me tell you, your mobile phone when charging takes few milliamperes of current. Yes, milliamperes. The AC, the heater, your kettle, water kettle, all those things takes a few amperes, like 2 amperes, 3 amperes, 5 amperes, or even up to 10 to 15 amperes, not more than that. But lightning which strikes the earth, which is very dangerous, that is thousands of amperes. That is why it is considered to be very dangerous. Got it? So a charger typically in milliamperes, your laptops milliamperes, but you know, heaters and all of that go in amperes, and lightnings in thousands of amperes. That is what you should understand, the scale of ampere. Now to give you an example of this, just say, for example, these kind of questions have been asked in the NEET previous year papers. They give you charge is equal to, let's say, t cube minus 2t square plus 5 coulomb. Question will be, find the current at time is equal to 1 second. This kind of question can come. So what you will do, you will see the given information and realize, oh, the charge is changing with time. To find current, I have to differentiate it. I have to take the derivative of this, dq by dt. Okay, no issues. Current is nothing but derivative of the charge, which means I have to take the derivative of this entire thing, t cube minus 2t square plus 5. What might be the derivative of t raised to 3? 3 comes here, power reduces by 1, so it will become 2. Minus 2 will come as it is a number. T square's derivative, 2 will come outside, times power will reduce by 1. 5 being a constant, the derivative is 0. So therefore, the current in general will become 3t square minus 2 2s are 4t. Now the question is at 1 second. So I1 will be, substitute the value of time as 1 minus 4 into 1. So what is the answer? 3 into 1 is 3 minus 4. which is minus 1 ampere. Now you will be scared, sir, I got the answer as negative, will I get negative marks? Don't be worried, you will see the options. If it says minus 1, you will just mark it. What does this minus sign indicate? It just indicates that whatever direction you had assumed is probably wrong. If you say this is the direction of current, actually the current is not that way, the current is going this way, having a magnitude of 1 ampere. That is what it means. Is that clear, everyone? Very good, Krishna. VS, Madhumati, excellente. Suganya, long time, I am very good. Suganya, yes, I was not able to take the classes when I was back in Pune. I was meeting all lovely students, just like you. Yes, correct. Moving on to the next concept. Electrical currents in conductors. Electric charge will experience force, okay. Now in this entire paragraph, I'll tell you what they have exactly done. So there are many lines in this section, entire section 3.3 before 3.4 going to Ohm's law. This entire section is talking about how exactly the charges move and what exactly conductors do in helping the current flow. Let's just go through it. Let's just read through it, okay, calmly, and then we will understand it, okay. First, let's read calmly. Don't worry whether I'm understanding or not, forget it. Let's just read through it. So when a charge will experience a force when an electric field is applied, if it is free to move, it will move in contributing the current. In nature, free charge particles exist like atmospheric strata, the ionosphere. However, atoms and molecules, the negative charges, which are basically the electrons, and the positive charges, which are the nuclei, are bound to each other. Hence, they are not free to move. Bulk matter is made up of many molecules. In fact, a gram of water itself has so many molecules. Now, these molecules are packed and the electrons are no longer attached to the individual nuclei. In fact, in some of the materials, the electrons will still be bound and they will not accelerate even if you apply a field. In some materials like metals, these electrons are practically free to move and they will, move inside the conductor when electric field is applied. If you consider solid conductors, then of course the atoms are tightly bound to each other. So the current is carried by the negative charge electrons, and there are, however, other types of conductors like electrolytic solutions where both can move. In our discussions, we only focus on solid conductors. Consider the first case when no field is present, okay. Before going here, let me just start underlining few things. An electric charge will experience force if an electric field is applied. If it is free to move, it will contribute to the current, okay. In some materials, the electrons will be bound. They will not accelerate even if the field is applied. Whereas in other materials, notably metals, some of the electrons are practically free to move within the bulk material. These materials are basically called conductors and they develop electric current when electric field is applied, okay. So that the current is carried by the negatively charged electrons, okay. We only focus on our solid conductors, okay. Consider the first case when no electric field is present and the electrons will be moving to the thermal motion, will collide with the fixed ions. An electron colliding with other ion emerges with the same speed as before the collision. However, the direction of the velocity is random. At a given time, there is no preferable direction of the velocities. Thus, on an average, the number of electrons traveling in any direction will be equal to the number of electrons traveling in the opposite direction. So there will be no net current. This is considering the first case when there is no electric field present and they will be moving due to the thermal motion, okay. I will just read it and then I'll explain, don't worry. Let us now see what happens to such a piece of conductor when field is applied. When electric field is applied, this is the next case when electric field is applied, okay. Now you take a section and you see that some positive charge which is distributed on one disc, negative charge on the other disc. We attach the two discs on flat surface of the cylinder. Electric field will be created in the direction from positive to the negative charge. The electrons will be accelerated, okay. They will thus be moving to neutralize the charges. The electrons, as long as they are moving, will constitute electric current. Hence, in the situation considered, there will be current for a very short duration and not after much time. We can also imagine, see guys, NCERT will try to complicate things, but wait a minute, Shreyas sir is going to decode this entire NCERT for you. We can also imagine a mechanism where the ends of the cylinder are supplied with fresh charges so that, continuous flow is there. In that case, there will be a steady electric field in the body. Okay, so imagine where ends of a cylinder are supplied with fresh charges to make up for any charges neutralized, so that in that case there will be a steady electric field in the body, and this will result in continuous current. This will result in continuous current rather than a short current. This mechanism by which you make a steady current is basically called as cells or battery. They are called as cells and battery. We shall study them later. All right. So what is all of this? Let's decode. Imagine there is a house. Imagine there is a house. This house, okay, this house is basically the nucleus. This house is the nucleus, which is basically positively charged. In that house, there are many kids, maybe 4 or 5 kids. Okay, these kids which are there, these tiny mini pandus which are there, okay, these kids are basically negative charges, basically the electrons. Now just imagine, maybe your favorite hero or heroine has come. Maybe Thalapathy Vijay came in the neighborhood that way, or maybe Dhoni came, okay, near your house, maybe in a coffee shop for some reason, or maybe some beautiful actress came. Okay, so what will happen is these kids are like, I want to go out of the house, I want to go to the house, I want to meet Dhoni, I want to meet this person, my favorite hero, heroine has come. They will try to go, but the parents will be like, no, you can't go, you have to stay in the house. So usually in an atom, the electrons are bound. They cannot go outside this door. Agree or disagree? But inside the house, they can keep moving randomly. They are running around like mad people. Inside the house. That random motion happens within the bounds of that vicinity of that atom, but not far away from the house or that atom itself. That random motion of the electrons is associated with the temperature or the thermal energy. So when you take, let's say, copper or gold or aluminum, inside that so many electrons are there and they are moving randomly here and there, they are colliding. That random motion is associated with temperature. If you heat it up, there is more randomness. Imagine there is more heat in this. These kids are running around like crazy. They are going nuts. They are going mad. Is that clear? Okay. Now imagine many such houses. Imagine many such houses. Obviously, with houses come many such kids out here. Many such kids. If, for example, our beautiful Champa has come, all these Pandus are at home. Okay, this is a beautiful Champa. All these kids are like, all these Pandus are like, I want to meet my hero, I want to meet my heroine, I want to meet my superstar. These houses are not letting them go. This Champa, this superstar is like that external field. What is that Champa or that external superstar? Like the field, electric field. What does electric field do? Electric field applies force on the electrons. Is that right? Force on the electrons. So now what happens is, if it's a non-conductor, basically an insulator like rubber, wood, paper, marble, stone, soil, bad conductors, no matter which superstar comes, no matter which Champa comes, these electrons can never leave their houses. The kids will be crying, but they can't leave. So for non-conductors like rubber, etc., the electrons can't leave the atoms. They cannot flow even if there is an electric field, because of which they do not conduct electricity. But in a conductor, the parents are little lenient. Okay, your superstar has come, go. Here, take some money, okay, enjoy, okay, eat something. Okay, maybe drink some juice. Okay, here have some chips. So the parents gave some money. Okay, go meet your superstar. So these kids run and meet the superstar. So there is a flow of charges. These electrons flow. So there is a flow of charges because of an external influence. And that's what constitutes current. Where does it happen? In conductors. Example, metals, copper, silver, gold, aluminium, iron. So all these substances, you will see the parents of their houses, basically the nucleus. The nucleus is lenient and they have let the electrons free to roam around. Now, if few of the kids meet the superstar, the other kids will think, already this superstar is surrounded with so many kids over here. What will I go and do? They will get demotivated. Already this Champa is giving bhav, is giving, importance to the few Pandus around whatever that star. So the other kids are like, okay, my role is not there. It's okay, Papa, I will stay at home. It's okay, Mom, here, take this money. I'm going to stay at home. So the other kids do not have motivation. But imagine one more Champa comes. One more Champa comes over here. One more superstar comes. Then the next few kids will get motivation and they will go towards the Champa. Is that right? But then again, other kids will be like, okay, already the Champa is surrounded by Pandus. I will not do anything. Then you need one more Champa. Imagine there is a continuous supply of Champa. Imagine there is a continuous supply of Champa. What will happen? Kids will keep coming. Kids will keep coming. Got it, my dear warriors? So, what they explain in the paragraph is that if you apply the electric field using, some plates or anything, then the charges will get attracted and then the charges are neutralized. After that, there is no current. But if you constantly maintain the electric field, if you constantly maintain the supply of electric field, how do you do that? By connecting a battery, a cell. Then charges always have that motivation because of that electric field to leave the nucleus. They are free and they continuously flow inside the conductor, and that's how current gets established. Is that absolutely clear what they have explained in these 3-4 ridiculous pages or paragraphs? I have marked all the important lines for all of you. This is the main thing what they have explained. Clear? Have you understood it? Are you able to visualize this now? What happens inside a conductor? Electrons, they want to leave, but they can't leave for a non-conductor like rubber or wood. But for conductor, they can leave, free to move. Once they move, the charges get neutralized. Then there is no motivation for the new electrons. So the current will be only for a short duration. So to continuously maintain the current, you need to continuously give the electric field. That external motivation has to be there. So that comes through a battery, a cell. You buy those cells, you connect it across a wire, continuous electricity flows. Okay, clear? Awesome. Yes, Pakka clear. Very good. Now let's come to basic Ohm's law. So now that we have understood what current is, Ohm's law is a law which was given almost like 200 years back, guys. Okay, and he said that whenever he applied whenever he connected a battery or a cell across different devices and he changed the battery's voltage or he increased the power supply, he found that the current was proportional to that voltage, and that is exactly what Ohm's law is all about. So a conductor through which current I is flowing and voltage V is the voltage difference between the ends of the conductor, then Ohm's law says voltage is proportional to the current, or the constant of proportionality is basically called R, which is the resistance. How much does it resist the flow of the current? The unit of resistance, the SI unit of resistance is basically Ohm and is denoted by the symbol this sigma over here. The resistance not only depends on the material but also the lengths, the breadths, everything, and we will see how it is determined in the next slide. So basically what Ohm said is that if you have some device and he passed different values of current. So he sees what is the current, and he also notices what is the voltage difference across the ends. First he saw when there is 0 volts, then there is 2 volts, then let's say there is 4 volts, okay, then let's say there is 10 volts. The currents that he saw, for example, no current over here, then let's say there is 0.5 current over here, then he saw basically 1 ampere current over here, okay, so then he saw basically 2.5 ampere current over here. He saw that the current is directly proportional to the voltage. And if you notice over here, if I write V is equal to I multiplied by R, take any value, for example, I take the value of 2, okay, is equal to current is nothing but 0.5 multiplied by the resistance. I will get the resistance as 2 by 0.5, which is 4 ohm, which is basically 4 ohm. So this tells me the resistance of this device is 4 ohms. If the resistance was more, then this won't be the current would be less. If the resistance is less, for the same voltage, there would be more current which would be flowing. That is exactly what Ohm said. Yep. All right. Very good. Now, this is only true for something called as ohmic devices. Ohmic devices, you will see later on in semiconductor chapter that there are non-ohmic devices as well which do not obey Ohm's law, which means if you increase the voltage, current increases but not proportionately. Suddenly there is a sudden jump, then it is not increasing so much. So that weird behavior can happen. At that time, imagine this happened, in 1828, the knowledge of semiconductors was not there. So he gave the law, although this law is only valid for mainly conductors, not for semiconductors. Is that absolutely clear, everyone? Adesh, obviously JEE Mains is tougher, but board is tough if you do not understand the concepts. Yeah. Now, how does it depend on the dimensions of the, how does the resistance depend on the material as well as the dimensions? So we'll come to that as well. So the resistance depends on material of the conductor as well as the dimensions of the conductor. How does it depend? That is what they have explained in these few paragraphs right over here. Now, what they have written down in these two paragraphs, I will just have a look at it, okay, and I'll explain and decode it for you. So first they take a single slab of conductor of certain length and area, then they increase the slab's length, and what happens is basically they put another slab along with it to increase the length, and they apply the same voltage. They find that the current has become less. That's because the resistances have become more, okay. So they conclude from here that the resistance is proportional to the length, and next time instead of placing one slab after other, they cut the slabs or place it besides each other. Then they find that the resistance has increased, and then they conclude that okay, resistance is inversely proportional to the area. So how they are doing this, let me tell you. Imagine this is the conductor. Imagine this is the conductor, and what they do is they have passed in some current over here because there is some voltage difference. So they find out what is the resistance, and the resistance comes out to be, let's say, V by I, because V is equal to IR, R will be V by I. Next time what they do, they take the same conductor, but they put another similar conductor in front of it so that the length becomes basically double. So now the length is double, or you can think as if there are two conductors side by side. What they find is, if they apply the same voltage now across this, the current which passes through this becomes I by 2. The current which passes through this will become I by 2. So this resistance, this new resistance will be voltage by current, So it will be V by I multiplied by 2, but V by I is nothing but R, so it will become 2 times of R. So the new resistance has become 2 times, and the new length was twice the old length. From this, what they concluded, resistance is directly proportional to the length of the conductor. Longer the conductor, more is the resistance. Is that absolutely clear, everyone? How they were able to conclude this? By putting another conductor, and if you put 3 conductors, the resistance will become 3 times, the current will become 1/3. If you put 4 conductors, resistance will become 4 times, one after the other. Now they did the same experiment, but this time they put another conductor besides it, another identical conductor besides it. So instead of one after the other, they put another identical conductor besides it like this, and they applied the same voltage, say for example, the same voltage like this. What they found was, now the current had 2 paths to go like this. In fact, the current became 2I. The current became double. So from this, if you find what is the new resistance, voltage is V, current is basically 2I. So it will be half into V by I. V by I is R, so it will be R by 2. So what they found is the resistance has become half when the area is 2 times the old area. From this, they concluded resistance is inversely proportional to area. Area doubles, resistance becomes half. Resistance becomes half. Exactly. So that is how they were able to finally write down. Okay, resistance is proportional to length, resistance is inversely proportional to area. Therefore, resistance is proportional to L by A. Therefore, I need a constant of proportionality. Instead of proportionality, I put a symbol called rho. What is this rho? This rho is that constant which is called as resistivity. Resistivity. Understand that. So this is called as the resistivity. This is resistance. This is resistivity. Resistivity is of a material. Aluminium will have some resistivity. Copper will have some resistivity. No matter where you find the copper will have the same resistivity. But resistance depends on resistivity, length and area. If you take more copper, the resistance might be more or less depending on whether area is more or length is more. But resistivity is a material specific property. If I take a long rod of copper, then the resistance will be more, but resistivity will still be the same. If I take a wide copper, maybe the resistance will go down, but resistivity will still remain the same. That is what they have written down right over here. So this is a very, very important formula, guys. R is equal to rho L by A, and this constant of proportionality rho depends on the material, like I said, whether it is copper, aluminum, etc. of the conductor, and very, very important, not on the dimensions. And this rho is basically called as resistivity. Okay, that is what it is. So if you write Ohm's law, instead of V is equal to IR, you can write R as rho L by A. So it will become I rho L by A. That is what they have done. This is not so important. If you know this and Ohm's law, it's more than enough. Till this point clear? Very good, Atlaru, Krishna, Madhumati, Chitra, Sukanya, understood? Clear? Shall we move ahead, my dear students? Everyone? Okay. Cool. Now they derive another expression called E is equal to rho J, and there is a very funny way they do it. See, V is equal to current into resistance, correct? What if I write resistance as rho L by A, and then they write current by area separately, okay, rho over here, and then that length they take it over here. Voltage per unit length, what is it? dV by dr. It is nothing but electric field. If you remember this definition which we have learned before, electric field electric field was negative dV by dr. So here we are just concerned about the magnitudes, don't worry about the minus sign. Rate of change of voltage with distance. So voltage per unit length gives me the magnitude of the electric field. What is this current per unit area telling me? This is telling me, listen, if you have a cross section, okay, and in that cross section, for example, some current is flowing through it versus the same current flows through a larger cross section. Here the current per unit area is more, here the current per unit area is less. So I get a term called as current density. So the current is more dense, more current density in this case, versus there is low density of current in this case, because the area is more for the same current. So this current per unit area is given a symbol J. So remember, this J is current density, which is I by A, guys, which is nothing but I by A. Very, very important. So that is how they get electric field is J rho. Electric field is nothing but J rho. That is what they have got right over here. So you might be wondering, sir, what is this electric field that we are talking about? This electric field is the electric field inside the conductor, which causes the free charges to move. Very, very important. Without this electric field, remember, this electric field is like that champa or that superstar, giving that motivation for those electrons to move. So that electric field is inside the conductor, which causes the motion of the charges. J, like I have told you before, is nothing but your current density. This current density will have a unit of ampere per meter square. How many amperes is going per unit area? That is nothing but your current density. Now this equation was completely in magnitudes, like you see the minus sign, everything was ignored, but actually it can be written down in the vector form. Now current density is actually a vector quantity, and you can rephrase this as J vector is your, or rather electric field vector is your J vector into rho, and then they define another quantity called as conductivity. Okay, so we'll come to that, but before that let's block all the important statements over here, and they write sigma is 1 by rho, which is nothing but called as conductivity. Okay, and they have also defined the current density vector over here. The current density which you have defined, the current through the unit area normally to the current is also directed along E. It is a vector. Okay. So now what have they basically told over here? Let me tell you. See, understand this. Okay, very carefully. Observe. This was our area. Let's say the current flowing through it was like this. The current value was I. Current density is a vector which is perpendicular to that area in the direction of that current. Okay, and it is a vector in this direction of the current itself. It is in the direction of the current itself. So that's how it has been defined. Now, if you talk about the conductor, if you look at the conductor, this, let's say, is our conductor. Inside the conductor, who moves Which charge moves, positive or negative? Nucleus does not move, electrons move. Which direction do they move? Which direction do they move? Think about it. Which direction do they move? Yes, they move opposite to the direction of the current. These electrons obviously move opposite to the direction of the current. This is how the motion of the electrons is. And that is the reason why the current was in this direction. Okay, that is how the current was here. So actually the electrons are moving in the opposite direction. So in which direction the electric field is applying the force? Obviously the force applied by the electric field on the electrons is in this direction. Hence the electric field itself must be in this direction, because electric field on a negative charge applies a force in the opposite direction. So hence electric field was in this direction. So can you see electric field vector is basically parallel to the current density vector, is parallel to the current density vector. So that is why this equation which we had, E is equal to rho J. Rho was your resistivity. Okay. It can be written down in vector form also, because the directions are same for J vector and E vector. If I put J bar here, there is no harm in putting E bar over here. It's fine. It's perfectly fine. Got it, everyone? Why I am able to put the bar over here? Because electric field is parallel to the J vector. Now what they do in the next step is they take this E bar and this rho which is there, they just put it over here. And they get J bar. This 1 by resistivity, they are calling it conductivity. So conductivity is 1 by resistivity. Meaning, if something is more conductive, it will have less resistivity. If something has more resistivity, it will have less conductivity. So they are just inversely proportional to each other. That's all. If somebody is less bad, that means he is more good. If somebody is more good, that means he is less bad. So they are inversely proportional. So it's just a way of looking at it in a different way. So this is then called as sigma, which is conductivity. These people come over here as it is and is equated to J bar. Is that understood? How this expression comes? And what they mean over here? Absolutely clear, my dear warriors? Cool? Very good. If you have understood it till here. Awesome. Now let's go to 3.5, where they talk about drifting. And then they have given some interesting paragraphs here, and okay, till here. Okay, these 3 pages. Let's have a look at it. Let's read it and obviously then let's decode it. Okay, cool. Let's start reading, guys. Start. An electron suffers collision with different things, but after collision it will emerge with the same speed in random direction. If you consider all the electrons, their average velocity will be 0. Very important line. All the electrons, their average velocity will be 0 since their directions are random. Very important. So if there are n electrons, the velocity of the ith electron at any given time is this, blah blah blah. So the average is 0. Okay, no need to by heart this. Consider now the situation when the electric field is applied. Electrons will be accelerated by this particular formula, and then if you take it for any particular electron, okay, the velocity after time t is given by kinematic equation. Final velocity is initial plus acceleration into time. Since Since starting with its last collision, it was accelerated with the acceleration given by for time t. The average velocity for the electrons at the time t is the average velocity of all the VTs, okay, the average blah blah blah, since immediately after any collision, direction of the velocity of an electron is completely random. The collision of the electrons do not occur at regular intervals but at random times. Let us denote tau, the average time between the successive collisions. Then over a time, some of the electrons would have spent more time than tau and some less. In other words, the time t will be less than t for some and more blah blah blah. Then the average value will be this, and this okay, you will get something called as the drift velocity. In this last result is surprising. It tells us that electrons move with an average velocity which is independent of basically independent of time, although all electrons are accelerated. This is the phenomena of drift, and this is called as the drift velocity. Okay, so again, this particular formula of drift velocity, very important. It tells us that electrons move with an average velocity which is independent of time, and this is called as the drift velocity over here. Okay, so what is basically explained over here? Let's understand. If you look at the life of any electron, it goes like this: hits somewhere, hits somewhere, hits somewhere. This is inside that, you know, solid. It is moving randomly over here. So there is random motion of the electron, In fact, if you look for a decent amount of time, let's say 1 minute or 2 minutes or maybe 30 seconds, you will see on an average these electrons have zero velocity. These electrons have zero average velocity. So I can say the average velocity is basically zero because the displacement is zero for a decent amount of time, for an, you know, time interval. For a time interval, if you look at it, on an average, the velocity is zero. Okay. Now, if it was a stationary electron, and if somebody applied an electric field like this, that electron will experience a force in this direction, because of which it will end up accelerating, and that force will be nothing but the charge. Let's say the charge is E multiplied by the field, So hence now there will be acceleration, which is given by force by mass. So the acceleration will be force divided by mass. The force itself is capital E into small e, field into E. Because of which what will happen, the velocity will continuously what? Increase. After some time it will become 2 meters per second, then 10 meters per second, 20, 40, 100, 1000, 1 lakh, if the field is continuous. There is nothing to stop it. But inside a conductor, even when you apply the field, because you connect a battery or a cell, it does not continuously increase the speed. After some time, what happens is, this electron which was being accelerated, yes, the velocity might increase. Yes, the velocity might increase for some time, but it will collide. It will collide with something. It loses everything, and again it starts from rest, again increases the velocity, maybe for a longer time, and again now collide, and then again it starts increasing the velocity. Maybe the collision happens sooner here, again it starts increasing the velocity. So if you see, it's like going inside the traffic. It's not on an expressway which is continuously accelerating. So it increases the speed, thop, okay, full, one tight slap it gets, again it accelerates, thop, slap it gets, stops. That slap corresponds to collision. Every time it collides, loses its velocity. Again it accelerates, again loses its velocity. So if you see, it is not continuously increasing the velocity, rather I would suggest that it is on an average going with some average velocity. It is going with some average velocity. It's basically getting drifted slowly, and all of this was happening because of the field which was pulling it, accelerating it, and the collision which was again bringing its velocity down. So this is basically called as the drift velocity. What is this called? This is called as the drift velocity. Did you understand what is the meaning of this word drift velocity, VD? Everybody till this point? Yep. Very good. Excellent. Now what they say is, see, if you look for only one atom, this final velocity is basically initial velocity plus acceleration into time. But if you look for many atoms, this final velocity on an average, which is initial velocity on an average plus acceleration into time on an average. This velocity after the collision is going to be 0 on an average. This velocity on average is going to be 0. This final velocity on an average by which they keep on moving, that is basically your drift velocity, Vd over here. Acceleration, we just figured it out right over here. It is E by m. It is nothing but E divided by m. This time, sometimes longer, sometimes even longer, sometimes shorter. It accelerates for more, less, depends. But on an average, if you take that time over here is called as tau, which is called as your relaxation time. Relaxation time means it gets slapped, thup, again it accelerates, slapped, again it accelerates, thup, slap. So it is relaxing, one slap, now no slap, it is accelerating, thup. So that time on an average is called as relaxation time. Got it, my dear warriors? Clear? So that is how they get this expression, Vd is equal to E by m tau. Vd is equal to E by m tau. Where did it go? E by m tau. Sounds only so nice, no? To say E by m tau. Vd is equal to E by m tau. Okay? E by m tau is equal to Vd. Vd is equal to E by m tau. Maybe some jingle will be made. If somebody is a musician, you can make some nice music out of it. Vd is equal to E by m tau. Cool? Understood? Clear? Vd is equal to E by m tau. I feel like saying it again and again. It sounds so interesting. Vd is equal to E by m tau. Great. Now, moving ahead. What have they done? Such nice paragraph they have written. Something and all they got. And don't worry about this. I'll explain you. They have not mentioned anything significant, but they have done some derivation in a very textual format. I will explain everything over here. And then they get current density in the form of relaxation time. Okay. How did they do it? See, I'll explain this before going ahead. Imagine you take a conductor of some area, some length, okay, and it has some amount of current. So basically some charges will go through this cross section from here to here in a time of delta t. And as they are moving with a velocity on an average of drift velocity. Okay. How long does this session take? As long as it takes to complete this. Okay. If needed, we'll break it down into parts, but okay, as long as it takes to complete this, guys. Okay. If needed, we'll break it into parts also. All right. So now, my dear students, over here, okay, observe this carefully. In this small time interval, these charges cross this cross section. So can I say that the amount of charge flowing upon the time taken being the current, I can say that charge upon delta t is equal to I, rather Q is equal to I delta t. Q is equal to I delta t. This is one way of looking at the charge. Second way is, this conductor will have some free electrons per unit volume. If you take a good conductor, it will have many free electrons in 1 unit volume. If it's a very bad conductor, not so many free electrons per unit volume. So I define a number called as N, which is number of free electrons which are participating per unit volume. So can I say this N is equal to the total number of electrons upon the total volume. Now the total volume, can I say it is area multiplied by the length? Area multiplied by the length. Okay, perfect. Now what I will do is that I'll think if each electron has a charge E, the total charge which I was talking about, this Q, will be the number of electrons multiplied by each charge has a charge E. So this Q which was there inside, which flows through that conductor, will be number of charges into E. But what is that number of charges, which we can see right from here? It is nothing but NaL. So guys, Q is equal to NaLe. Q is equal to NaLe, Nali. So, but Q is also I delta T. Q is also I delta T. So therefore, I can write it as NaL and then E over here. Is that absolutely clear, my dear warriors? Everybody till this point clear? That is what they have done in this particular thing. Current into time on this side and NaLe. Now what they do later on is that instead of writing length, length they write it as speed into time. Speed multiplied by time. That's it. And here on the left hand side, you still have I delta T. So this length which is there, what they have done? This length which is there, they have written it down as speed multiplied by time. Length they have written it down as speed into time. So now what and all will get cancelled? Delta T and delta T got cancelled. That is what they do over here. Okay, they will basically cancel that delta T and delta T, and they bring down this particular area below the current, the rest of the things as it is, N, Vd and E. N is there, Vd is there and E is also there. What is I by A? It is nothing but J. What is drift speed? Drift speed, we just got it over here. It is EE by tau m or EE by m tau. Okay, E by m and the whole thing multiplied by tau. So EE by m, the whole thing multiplied by tau, and this E is as it is. So from this we get J is equal to N E square E by m and tau. That is the formula. Is this derivation clear now, how they got it? That's the derivation, guys. That is exactly what they have obtained right over here. Okay, that's all you should know. Okay, so I've explained this in a very simple manner. This is paragraph manner. You will not understand it if you read it also. Rather, I have tried to keep it as simple. I found the charge here. I also found the charge other way, and then I just equate it from here and here. Okay. Okay, so at this particular step, I have equated it. Cool. Let's go ahead. Now, they also say that this is exactly Ohm's law if we identify the conductivity as this blah blah blah. So what they have done over here is this is J, and remember there was an equation. Where did it go? Okay, let me write it down over here. J is equal to NE square tau by M, NE square tau by M, NE square tau by M into E. But long time back, we also wrote down J is equal to E multiplied by sigma. If you have forgotten where we wrote it down, right over here. J is equal to E multiplied by sigma. We wrote it down just some time back. So comparing these two, so just by purely comparing both of them, what do you get? Just by comparing both of them, sigma is equal to NE square tau by M. NE square tau by M. That is what they have also done. NE square tau by M. Clear? Okay. So that is what they have obtained. Shall we go ahead, my dear students? Shall we go ahead, my dear warriors? Ready? Cool. Okay. Great. Let's go ahead to some questions. Okay, there is a question over here. Now, how to solve this question? I will definitely help you out with it. So they say that there is a wire of some cross section, some current, and each atom contributes 1 electron. Density is also given, atomic mass is also given. Compare the drift speed, thermal speed, and speed of propagation of electric field at what causes. Okay, fine. Now see guys, over here what and all values are given to me. I'll just write it down. First of all, I am given the area of cross section. Area of cross section is 1 into 10 to the power minus 7. So 10 to the power minus 7 meters square. Then current is 1.5 amperes. Current is 1.5 amperes. Then each copper atom contributes 1 electron. Okay, density is given as 9 into 10 to the power 3. Density is 9 into 10 to the power 3 kg per meter cube. Atomic mass number also they have given. How much is it? 63. So 63.5 grams are there per mole. Okay, that is what they are given. And what we have to find is basically the drift speed and other things. Before solving anything else, this third part, speed of the propagation of the electric field in the conductor. Yeah, sorry, the second part, which we can do very easily, this part. What is the speed at which the electric field moves inside anything? Electric field, guys. If you remember light is an electromagnetic wave. An electromagnetic wave or light travels at what speed? The speed of light. So electric field, magnetic field, if there is a charge, zoop, the information will travel, the field will travel everywhere at what speed? Speed of light. So this answer, the speed of propagation of the field along the conductor which causes the drift motion should be the speed of light. I think the answer should be mentioned as it is. Yes. Yes. The electric field travels exactly at the speed of light. Okay, which is nothing but 3 into 10 to the power 8 meters per second. So electric field travels at the speed of light. So that is that particular answer. That is that particular answer, and we have done this. Now let's go to the thermal speeds of the atoms versus the drift speed. So for the drift speed, I think I will need all this information. How do I do this? How do I solve for the drift speed? Think about it. I feel to find out the drift speed, what do I need? What do I need? There is a beautiful equation actually. Which comes down as current is equal to NVDR. This equation, although it is not there in NCERT, please remember it. It will help you and it will solve the problems in a much simpler manner. So remember this formula. So because of which drift speed will be current multiplied by NEA. Now you will be like, sir, what is the value of the current? The value of the current is nothing but 1.5 ampere. Okay. What is the value of E? It is 1.6 10 to the power minus 19. What is the value of A, sir? Area is basically 10 to the power minus 7. What is this small n, sir? It is not given to you. That value is basically not given to you. So how do I find this small n becomes the next challenging part. This is number of free charges per unit volume. Since it was mentioned each atom contributes 1 electron, can I say it is basically the number of atoms upon the volume. Now volume can be written down as mass. See, mass by volume is density. So volume is nothing but density divided by mass. So mass goes on the top. Density is mass by volume. So volume becomes mass divided by density. Sorry, I think I missed this. I wrote it perfectly, no? Density is mass by volume. So volume will be mass by density. I wrote it ulta, guys. I'm so sorry. This should be the mass and here should be the density. Okay. Now once I get this, yes, NVIDIA, graphics card company. Yes, is it there in NCERT? No, it is not there directly in NCERT, but you can use it. Okay, it is not there in NCERT, but use it. You can get it by again modifying these drift speed formulas. If you modify these drift speed formulas now, you again get the same thing only. Okay, so you don't have to worry about the derivations, but just remember NVIDIA, graphics card company. Now the mass which is there, mass can be written down as mass of each atom into the number of atoms. I can write it down as mass of each atom multiplied by the number of atoms and this density will come over here. This n and this n cancels. What will be the mass of each atom? That will be nothing but your molar mass. This density is on the top only. Molar mass divided by Avogadro number. So hence this small n becomes Avogadro number multiplied by the density, whole thing divided by the molar mass. That's it. So this thing is not mentioned, but you know they are using it in NCERT. So that is why I am explaining this to you, how this came. Once you get this, small n can be easily found out as 6 into 10 to the power 23. Density is how much? 9 into 10 to the power 3. Molar mass, be very careful. It is grams, so 63.5 converted into kg by multiplying by 10 to the power minus 3. So that will be per mole. That's it. So I think you will get the answer from this. So whatever value of n you get, right, from here, so just substitute it over here. Just substitute it over here, and that's how you finally get the drift speed. That's how you finally get the drift speed. Is it clear? Yes. Okay. And this value comes out close to 1.1 millimeter per second. This value comes out close to 1.1 millimeter per second, guys. This is very small. Okay, as expected. Okay, don't expect the electrons to move with hundreds of meters per second. They will move very slowly, very slowly. But the electric field gets sets up instantly, speed of light. That is the reason why when you turn on something, although the wire might be long, it's not like, sir, the electron is moving at millimeter per second, sir. It took 5 hours for the electron to reach the fan. So when I turned on the switch, sir, after 5 hours the fan turned on. No, it turns on instantly. It turns on instantly because the electric field reaches there and all the electrons in that wire are moving at a very slow speed. Everywhere it is moving instantly, but at a very low speed. Keep that in mind. And then there was the second part of question which talked about what is the speed of those electrons which are moving here and there. That is usually the thermal speed, which you will learn in thermodynamics of 11th standard. That is of the order of few hundreds of meters per second. There the Boltzmann constant comes. You don't have to remember it as such, this particular thing, but in thermodynamics you might have learned kinetic energy is equal to 3 by 2 kT. Temperature is given, Boltzmann constant is given, half mv square is equal to 3 by 2 kT. From that you can find that speed. Okay, but you should know it is, in the order of few hundred of meters per second. So these electrons move randomly few hundred of meters per second, but as they move randomly, they are moving ahead very slowly, 1.1 millimeter per second. So they move really fast like this, but they slowly drift like this. After few minutes, they slowly go here, they slowly go here. They are moving very fast, but their effective output is that they are moving slowly, drifting slowly at few millimeters per second. So that is why this question was even there, to compare 3 different speeds. The first one being the drift speed, which is in very small values. Then you have your actual speed of the electrons, which is decently large, and the final speed was your light speed, which is very large. I hope this is clear. Cool. Awesomeness. Let's go to the next thing. Let's go to the next example. In example 3.1, the electron drift speed is estimated to be only a few for the currents. How then is the current established almost instantly? This answer I gave you that time only. How come the fan turns on or the light turns on instantly even if the electrons move in very small speeds like millimeters per second? It's because the electric field sets up really quick. It asks all the electrons throughout the circuit to start moving. Everybody is moving slowly, but they are moving. That's very important. That's why current begins instantly. So that's the answer of the first question. I hope this is clear. Okay. Next, the electron drift arises due to force inside the conductor, but the force should cause acceleration. Why do the electrons acquire steady average speed? This part I explained over here. How is it that an electron does not continuously accelerate, rather it goes with constant speed? It's because of the collisions. It increases the speed, loses the speed because of the collision. So that is why it moves with the average speed called as the drift speed. So that is the answer for the second question. Okay, that is the answer for the second question. Clear, everyone? Next one. If the electron speed is so small and the electron charge is small, how can we still obtain large amounts of current in the conductor? Electron speed is small, electron charge is also small. How come the current is in amperes? The reason for that, There are too many such charges even in a small gram of a conductor. Even few grams is like an Avogadro number, which is 10 to the power 23 number. So the charge is small, that's okay. The speed is small, that's okay. But the number of those charges, huge. 10 raised to 22, 10 raised to 23. That's the reason why the currents are in few amperes or milliamperes. That's the answer for the third question. Clear, everyone? Okay, all right. When electrons drift in a metal from lower to higher voltage, does it mean that all free electrons of the metal are moving in the same direction? So when we say current is moving like this, is it true all the electrons are moving opposite to the current? No. All the electrons are not moving opposite to the current. Few of them might be moving even in the direction of the current, but they are very few in number. Majority of them, so maybe 1000 are moving opposite to the current. Maybe some 3 or 4 are moving in the direction of the current. So as a whole, if you take the effective number of electrons, they are moving opposite to the direction of the current. I hope this is clear. I'm so glad, Lucky. Thank you so much. And I'm so happy that I'm your favorite teacher. Means a lot. And I'm so glad you love physics because of me. Means a lot. Thank you so much. Are the paths of electrons straight lines between successive collisions with positive ions of the metal in the absence of electric field, presence of the electric field? So what about the paths? Okay, how are the paths going to be? Now usually the paths are going to be straight lines. Even though the positive charges are there, they will cause small deflections, but they are too negligible. But usually they are straight lines between one collision to the next collision. So they go like this, collide, go like this, collide, collide, collide. But due to the nucleus, there will be a very small deflection, but not so much, and approximately straight lines. Okay, so all these same answers are written down over here in your NCERT as well. All right, let's go to mobility, guys. Let's complete this. Let's do the resistivity part also. Okay, all right, resistivity part also. Let's do this. Okay, now they have defined a new quantity called as mobility. Mobility means if I connect a battery, how fast are these electrons drifting? For the same battery, meaning a field is applied, if they are moving very quick, they are very mobile. If they are not, they are less mobile. So they defined it as drift speed by field. If their speed is large, that means their mobility is more. If I have to apply more electric field, that means I have to push them more. They are very lazy, so they are not so mobile. So mobility is less. That's the reason why mobility is defined. Mobility is defined as the drift velocity per unit field, electric field. Okay, per unit electric field. Drift speed formula we already know, it is E tau E by m. So if you substitute it over here, mobility will become just E tau by m. Okay, so mobility will just become E tau by m, because remember drift speed was E tau E by m. This E and this E can cancel out, and that's why you will just be left with this. So this can be also the formula, where T is the relaxation time or the average time of collisions. So this is something which you should know, which is given over here. This part, if you remember, I had explained it while explaining Ohm's law itself. Let me go back. Let me go back. Where is Ohm's law? Where is Ohm's law? Where is Ohm's law? Yes. I told you this law is only valid for conductors, which is basically ohmic devices. There are devices where voltage is not proportional to current. That is why they have mentioned about this, which is basically the limitation of Ohm's law. There are some deviations. Some materials do not obey proportionality. They have some non-proportional behavior. And such places, they are said to be non-ohmic devices. So very clearly mentioned over here, Ohm's law has been observed to be followed by many materials. There are devices where voltage and current are not proportional to each other. There do exist materials and devices where the proportionality does not hold. They are non-ohmic devices. Okay. This happens, for example, in a diode, which you will study in this chapter, chapter 14. That's basically semiconductors. So semiconductors are a good example of materials where Ohm's law is not obeyed. Okay, something which you should be aware of. They have shown how the current and voltages change. This is for a diode. You can see it's crazy, the voltage and current relationship. Then it is like this. It's very, very crazy. It is definitely not proportional. These are just graphs given. Then there is a material called as GaAs, gallium and arsenic. How does the current change with voltage? It's even more crazy. It goes up, then even comes down, again goes up. So we can see again non-proportional behavior. Okay, so they have just given examples. Please remember these graphs. They might just ask you which of the following graphs is the behavior of voltage versus current for GaAs. Some options will be given. If you know this graph, it is there in NCERT, you will immediately tick mark the correct option. Same thing for this. This you will learn in chapter 14, so don't worry, semiconductor chapter. Cool? Clear? All right? Great. Okay, so they have just mentioned what is Ohm's law where it is obeyed, and we'll be mainly studying those devices where Ohm's law is obeyed. Okay, that's fine. Now again they come back to resistivity of different materials. The materials classified as conductors, semiconductors and insulators are based on the resistivities and of increasing values. So if you talk about conductors, which are basically metals, they have very low resistivity, obviously, in the range of this much, 10 to the power minus 8 to 10 to the power minus 6. Obviously metals are conductors, so their resistances should be less. Resistivity also depends on the material, remember that. So they have very low resistivities, which kind of makes sense. Then you have other materials like which are insulators like ceramics, rubber, wood, plastic, paper, etc. They will have very high resistances, something like 10 to the power 18 times greater than the metals. So it's much, much larger than the metals. In between both of them, you have basically semiconductors. They have decent resistivities, but the funny part is their resistances, change with temperature and also with what kind of materials are added in it. So we'll study that in the separate chapter. Don't break your head. How can resistance change by adding some amount of some impurity in it? That is called as doping. That doping you will study in chapter number 14. Don't worry about it right now. But it also depends on the temperature. Semiconductors like, silicon, germanium, their, resistivities also depend on the temperature and also something on the impurities, which is called as doping, which you will be studying later on. Now, how does it depend on the temperature is what we are going to study. How does it basically depend on the temperature? Now, usually, if you take a conductor, what happens is, when you basically heat it, what happens is these electrons which are there, which are going randomly, these electrons which are there, their thermal energy increases. So what happens is their collisions increases. Because of the collisions which are increasing, what will happen? They are colliding very frequently, guys. They are colliding very, very frequently. That means they will not have enough speed. Their relaxation time is less. Let's go back a little bit to see what happens. Let's see what happens, guys. Over here, maybe. Yeah. The time will be less. Oh, sorry. Where did it go? Here. Their time will be less. They will collide very frequently. So relaxation time will be less. What will happen to the conductivity? Conductivity will decrease. So resistance will increase. They will collide more frequently. Time will reduce. Less time between every collision. So conductivity will decrease. So resistivity will increase. Hence, you will basically notice that the resistance will increase. Is that clear? The resistance will increase. But for semiconductors, it is exactly opposite. Why it happens, we'll study that later on in that separate chapter. Don't have to break your head now. But remember, for semiconductors, it is different. How does it change for a conductor? That formula is given right over here. The resistivity is rho naught 1 plus alpha delta T, where rho T is the resistivity at some temperature. Rho naught is the resistivity at some reference temperature, let's say T naught, and alpha is basically called as the temperature coefficient of resistivity. This implies that when you plot the graph, it would be a straight line, and at temperatures much lower than 0 degrees, the graph however deviates. Okay, thus this can be used an approximate limited range. Okay, fine. Now from this, it should be clear that if on the horizontal axis you plot temperature, this is your temperature, this is your resistance, the graph should probably look like this. As you increase the temperature, the resistance will also increase. Makes sense. Usually the graph is not a straight line, it is a slight curve, but if you take a small range, it approximately looks like a straight line. So for a small decent range of temperatures, it is approximately a straight line. Otherwise, it is slightly curved. It is slightly non-linear. It is not a straight line, it is non-linear. So that is why for small ranges, the graph will be directly dependent on the temperature. So you can see temperature is there here, not T square or T cube or root of T. All those things are not there. Rather, only direct single power of time is there. That is what it is. Yes. I hope this is absolutely clear. Rho naught 1 plus alpha delta T. This equation is very, very similar to, if you remember, final length is initial length 1 plus alpha delta T. Where did you study this equation? If you have studied 11th standard physics, you will remember this was linear expansion of solids. You heat a solid, it will expand or contract. Exactly. So same kind of expression is even there for temperature, dependence on the resistance. So the resistivity at any temperature is resistivity at some reference, okay, into 1 plus some constant into the change in the temperature. This is called as your coefficient of thermal resistance. Like you had coefficient of linear expansion, alpha, beta, gamma. This is alpha, but for resistances. Exactly. Okay. I hope this is clear. Okay, I have reduced the thickness of the pen. Don't worry. have reduced the thickness of the pen. Clear, everyone, till this point? So that is why this expression has come. And by the way, I have also mentioned over there also that it is approximately a straight line for a small range. Thus this equation can be used as an approximately over a limited range of temperature around any reference temperature, whereas the graph is an approximately a straight line. Approximately a straight line. And they have given that examples also. See this. Here they have given the example of copper, how the resistivity changes with temperature. You can see it is non-linear. But if you take a small range, it is straight line. Straight line. Another straight line. But big range, no. So from 20 to 30, yes. 20 to 50 also is okay. But 20 to 500, then I feel it's a problem because it's a huge range of temperature. You can see it's for decent temperatures. Whereas for nichrome, it is almost like a straight line. There are not many deviations. This is for semiconductor. This is very weird. Instead of increasing the resistance goes down. Why this happens? We will see it in that particular chapter, not here. But you should know that it is weird. Instead of increasing, it decreases. That's why there is a dedicated chapter only for that. There is a dedicated chapter only for that. Okay, great. Some materials, okay, magnitude and constant, these materials are thus widely used in wire, blah blah blah, would change very little with temperatures, unlike metals, resistivity of some, okay. Okay, so this special example of nichrome is what you should know. Nichrome, you can see it is a constant line. It is almost like a straight line. Oops, what just happened? It's almost like a straight line. So unlike copper or maybe aluminium where the graph is non-linear for a wide range, here it is a straight line. That is why they have clearly mentioned some materials like nichrome, okay, you can see there is hardly any dependence, very weak dependence with the temperature, and that is why they are usually used, you know, they are widely used in wires because you know how the temperature will affect the resistance. It's a linear relationship. Okay. This particular part, like I have been telling again and again, resistivity of semiconductor decreases with the temperature. This you will study later in chapter 14 of semiconductors. Don't worry about it right now. Okay. As we increase the temperature, I think this explanation I already gave. What happens? Okay. If you increase the temperature, collisions increase, relaxation time will go down, so conductivity will go down, and that's why resistivity will go up, because the number of collisions go up. That is something which I explained right over here, why the resistance increases. They have explained it right over here. So mentioning it here again. Okay. As we increase the temperature, the speed of the electrons, okay, increases. So frequent collisions, so the average time of collisions reduces. Okay, something which you should understand from this, which I have explained right over here, how heating it increases the temperature, increases the collisions, reduces the temperature, hence increases the resistance. That is what they have explained over here. Same thing again. Cool? Great. Okay. Well, this is fine. Okay. Now, this part, what they say is, N is not dependent on the temperature to any appreciable extent. Hence, the value of time plays a role. Whereas for semiconductors, N changes, and that's why you will see resistivity also depends on that. Okay. Now, if you notice this equation, the resistance not only depends on the time, but also on the number of electrons which are free. But when you change the temperature, this N does not change. Meaning, if you take copper, if you heat it, don't expect more free electrons will come. Getting my point? If you take copper, aluminum, which are conductors, if you heat it, if you heat copper or aluminum or gold, don't expect there are suddenly more number of electrons. Already it has done enough. It won't give new free electrons. So that's why for conductors, you will see it is generally not dependent on N. But for semiconductor like devices, which you will again study later on, you will see this changes drastically. This changes drastically upon heating. N changes. So resistivity depends on N also. That is what they have mentioned. So again, an important point regarding conductors, N is not dependent on the temperature. In metals, basically conductors. Basically conductors to any appreciable extent. And okay, but this is an exception now. This is an exception now for semiconductors. For insulators, semiconductors, N changes with temperature. N changes with temperature. We'll come to that again in chapter 14. Don't worry, we'll study that later on. Today only let's focus on conductors, and that is what they have also told somewhere over here. See, in most of these chapters, we will study currents in materials that obey Ohm's law. Very, very important, guys. We study currents in materials that obey Ohm's law, which means basically conductors. So except for that semiconductor chapter, everywhere else we study normal devices like conductors. So you increase the temperature, resistance increases, Ohm's law is obeyed, okay, everything is smooth. That is what they have told also clearly. Okay. There is a toaster which uses some wire. Some small current passes and the resistance is found to be this much. When the toaster is connected to this supply and there is some new current, what is the temperature of the nichrome element? The temperature coefficient is also given to us. Read the question again and again, and let's see how do we solve this particular question. Okay. Now here obviously resistance must be changing, because you can see the current has changed, and because of that I feel you should be able to use the formula for how resistance changes with temperature, and then you can find out what might be the new temperature. So ready to solve this? Ready to solve this question? Usually our equation used to be resistivity is original resistivity 1 plus alpha delta T. But there is no harm in replacing resistivity with resistance, but then make sure here also you put resistance only. There is no harm in this. Now resistance is voltage by current. Voltage is I think the same. So voltage by the current at time t, voltage divided by original current 1 plus alpha delta T. Do you see that this voltage and this voltage just cancelled out, and I get this equation. I think I know the current at time t, at some new temperature. What is the current? When a small current passes through it, the resistance is found to be this much. For this much supply, the current settles, and oh, I can't cancel the voltage, my bad guys. So sorry, because voltage only initially is given. My bad, sorry. What they have given is at room temperature the resistance is given, so R0 is given to me. At some new temperature, for that voltage the new current is given, so voltage at some temperature and current at that temperature is given to me. This is my complete equation. Now it's just about substituting values. 230 volts, this much current is at that new temperature, so put 230 over here. Current is basically 2.68. Original resistance 75.3. 1 plus alpha is also given 1.7 10 to the power minus 4. into delta T. What is this delta T? Actually, final temperature minus original temperature, which is 27 degrees Celsius. So from this, you will get the temperature. The temperature comes out to be some 847 degrees Celsius. It comes out to be 847 degrees Celsius. Now, if you look at the solution given in NCERT, you will get 100% confused. But if you look at my solution, it is very simple and elegant. Very simple and elegant. I just said this is the resistivity formula. So resistance formula will also look similar. Old resistance already given. New resistance indirectly given because voltage and current is given. Oh, now I know this. I just need to find what is the new temperature. Got it? Everyone? Yes. I hope this is clear. I hope this is clear. Okay. Let's go to the next question, maybe, or next concept. Okay. Resistance of a wire is 5 ohms at steam point. At ice point is 5 ohms and at steam point is this much. When it is inserted in a hot bath, the resistance is this much. Calculate the temperature of the bath. Very interesting question, guys. Very, very interesting question. See, one thing we know, resistance for a decent range is going to be like a straight line for a decent range. Ice point means 0 degrees Celsius. Steam point means 100 degrees Celsius. Means 100 degrees Celsius. At ice point, what is the resistance? 5 ohms. Steam point, what is the resistance? Where is it? 5.23 ohms. They have asked you now if the resistance somewhere is 5.795. That means it is much beyond than this. Somewhere over here maybe. This is 5.795 ohms. Then what is the temperature? Then what is the temperature? That is what they have asked. Is that absolutely clear? What the question is? Now, one way to do the problem is using equations. One way of solving the problem is using equations. Other way is using straight line equation, but don't break your head on the straight line equation. Let's just use resistance at temperature T is original resistance 1 plus alpha delta T. Let's rearrange. RT by R0 is equal to 1 plus alpha delta T. Okay. So RT by R0 minus 1 is alpha delta T. Take R0 on the top. RT minus R0 divided by R0. Bring that delta T below is equal to alpha. Why did I write this? Because alpha is not given to me in the question. Alpha is not given to me in the question. That is the reason why I did this. Now, whether I do from here to here or from here to here, change the temperature from here to here or here to here, alpha should be the same. So for this part, the yellow part, final resistance would be 5.23. Original resistance was 5 ohms. Divide it with the change in the temperature, 0 to 100, the change is basically 100, multiplied by the original resistance. Original resistance was 5 ohm. That is for the yellow part. If you do it completely for that orange part, including right from here, final resistance is 5.795. Old resistance is 5 ohms. Whole thing divided by change in temperature. Change in temperature means T minus 0. So T minus 0. This is old resistance. Old resistance is 5 ohms. Do you see everything in this equation I know except for T? Solve this, I will get the value of temperature. Did you understand what we just did? Alpha was not given, so first I wrote down what alpha is. Then I wrote this equation 2 times, one here, but for different ranges. First for this and then for the whole thing. That's all. So from this, I get the value of temperature as 345.65. 345.65 degree centigrade. Clear how to solve this? Isn't this method much simpler? Isn't this method much simpler? Yes or no? Yes or no, guys? Correct? Very good. Great. Starting off with electrical energy and power. Consider a conductor with certain endpoints. I will read it for you. Some important things will underline and I will obviously explain it to you. So imagine it is moving from one point to the other. Current I is there. At some point A and B, the potential is VA and VB. Since the current is going from A to B, always current goes from high to low voltage. So that's why VA is more than VB. And assume that the voltage difference between them is V. If some charge goes in time delta t, then the potential energy at that A by definition will be charged into voltage and at B will be charged into voltage. So the change in energy will be a charge into potential difference. But charge flown is I delta t, so then they say that the charge moved without collision through the conductor, their kinetic energy would also change the total energy. Conservation of total energy would imply that this, hence this, and then they say thus in the case charges are moving freely under the action of electric field, kinetic energy would increase. However, we see average the charge carriers do not move with acceleration but with a steady thing. Okay, 1 second. Let's underline important things. This is the voltage difference. The charge flown is basically I delta t. Okay. So if the charge moved through the conductor without collisions through the conductor, their kinetic energy would also change so that their total energy is unchanged. But this is very important. However, seen earlier, charge carriers do not move with acceleration but with a steady drift velocity. This is because of the collisions with the ions and the atoms during the transit. And this energy gained by the charges is shared with the atoms vibrate vigorously, conductor heats up, thus an actual conductor, the amount of, very important, thus in an actual conductor, an amount of energy dissipated as heat in the conductor during the time interval is given by this, and that's how they get this formula. P is equal to voltage into current, which you can also write using Ohm's law as this. Okay, now what do they really mean by this particular thing? See, I'll explain this to you. Remember, inside a conductor, imagine this is a conductor. It is the electrons which basically move. It is the electrons which basically move. And that movement happens because of the electric field. That motion of the electrons because of electric field inside of it. And we have seen that because of the electric field applying of force, ideally it should have accelerated with the force divided by mass, which means the velocity should have increased continuously. But it doesn't happen like that. Why doesn't it happen like that? Because these electrons don't just go in a straight line continuously, rather they continuously, collide with different atoms, other electrons here and there. So because of collisions, what happens is there is acceleration for some time, then they lose the velocity during the collision, and again repeat the process. Therefore they end up moving in an average manner. They move in an average velocity, which is basically called as your drift velocity. drift velocity. Everybody agrees with this? Everybody remembers this logic? Yep. Increase the volume, just 1 second. Is the volume less, guys? Less. Hello, just check it now. Is it fine? Is it fine, guys, now? Just check it out. Is it fine? Is the volume fine, everyone? Let me know. Just give me a thumbs up. Yeah, now it is fine. All right, pakka. Cool, cool. All right, just refresh in case of connectivity issues. Okay, right. Okay, so I had explained before that, the electrons end up moving with an average velocity called as the drift velocity. So, imagine there is a conductor, and if there were no collisions, then what would happen? That particular electron, the charge carrier, would continuously accelerate, and it would increase its kinetic energy. If kinetic energy is increasing, some other form of energy should decrease. So basically the potential energy will decrease. So the potential energy basically got converted into kinetic energy. But we know the velocity does not continuously increase. Rather, it maintains a steady speed, which means all the potential energy that it gains doesn't go in this path, it doesn't go in the kinetic energy, it basically is ending up lost. It is ending up as a loss of energy, it is lost as heat. So this is exactly what happens. So whatever potential energy it loses, ideally it should get converted into increase of the speed, but even before it reaches very high speed, what happens? It ends up colliding. So it loses in the collision, and when it collides, what happens? The molecules begin to vibrate, and these vibrations only are nothing but thermal energy. What do you mean by when something is hot? When something is hot at the molecular level, the molecules are vibrating more vigorously. They are rotating, twisting, moving here and there. So when there is more randomness, more energy, then thermal energy, basically temperature is more. If it has less heat, less temperature, the molecules are pretty much, chilled out. They are not moving so much, very less vibrations. So hence it is said that the loss of the potential energy is going as heat. Is that absolutely clear? So in order to find how much heat is lost as heat during collisions, so basically this particular heat loss per unit time is called as the power loss in the conductor. This is called as the power loss inside that particular conductor. Okay, I hope till this point everybody is clear why power loss happens in a conductor. You pass a current in any wire, any conductor, any resistor, any device, there is always some power loss. Well, it depends on the current and the resistance, but yes, why it happens, you should understand that. Okay, now in order to find that out, in order to find how much is that power loss, what they have done, they have found out how much heat is developed per unit time. That heat is basically the difference of the electrical potential energy. Now, electrical potential energy difference is the charge which flows into the potential difference itself. If you remember, this was there in electrostatics. Delta U is Q delta V. Okay. How much charge will flow? Charge is nothing but current multiplied by the time. and this is nothing but delta V divided by delta T. Delta T cancels, so it will become I delta V. But usually we do not write the voltage difference as delta V. Sometimes we end up writing it as just V. This V is just saying potential difference basically delta V. So that's how you get power is equal to current into voltage. Now this same derivation they have done over here, but NCERT loves to confuse students. They get pleasure. So every time a student get confused, they get 5 brownie points. They become very happy. Yes, we confused 10,000 students today. Okay, I don't know, maybe they derive some pleasure. So the way they have explained it, fine, it's good for teachers, I understand it, but Pavam kids, yeah, I mean just imagine Pavam, Pandus and Pachampas. It should be simple. It should be something like, any book should be something like which even a 6th standard student should understand, should develop interest. But that's why I am here. Your captain Shreyas sir is here, who is going to help you out and decode NCERT for all of you. So I have explained this to you in a beautiful manner, but we also know that, voltage, this voltage is nothing but current into resistance. So therefore I can also write P is equal to I into I is nothing but I squared into R. We can do one more thing. Current, we can also do one more thing. Current is nothing but voltage by R. So therefore power can be written down as V by R into V. Therefore power is equal to V squared by R. How did I get it? Using Ohm's law. So this is also correct. There is nothing wrong in this. This is also correct. Nothing wrong in this. This is also correct. Which one will you use? Depends. What is given? Voltage and resistance is given, you will use this. Current and resistance is given, you will use this. Current and voltage is given, you will use this. If they tell voltage is changing, resistance is constant. Voltage is changing, resistance is constant. Something you have to find, you will use this. Current is constant, resistance is changing, you will use this. Current is changing, voltage is constant, you will use this because it has current and voltage. Depending on which terms are being used, accordingly you will use one of these formulas. Okay, so that's what they have basically done till here. So that is the energy lost at per unit time. Where does this power come from, you might ask? So this power basically comes from some external source. So they have mentioned where does this power come from. The power comes from external source to keep a steady current through the conductor. Do you remember that Pandu Champa example of houses which I gave you guys last lecture in part 1? Where is it? Oh my god, yes, here. These houses are like the nucleus, the Pandus were like the electrons and some Champas came. So if one Champa comes, the Pandus run out of the house to meet the Champa. Those Pandus were like the free electrons of the conductor. The conductor is okay to let these Pandus leave that house. So that's why it's a conductor. Insulator won't leave these electrons, it will hold them inside that house, the house being the atom. Okay, now if there is a constant supply of Champas, Pandus will keep running out of their houses. So that's how you maintain that current. So you need to supply Champas, meaning you need to supply an external agent. In this case, you need basically nothing but a battery. So remember, my dear warriors, you need something like this. So these batteries, right? These batteries. So these batteries are exactly like these Champas. These batteries are like these Champas. Without this battery, these Pandus wouldn't have left their houses. The conduction of electricity wouldn't have even started. Yes. Is that right? Correct? So that is what they say. Okay. Yes, that's why Krishna is a very ideal, best student. I'm pretty sure Krishna enjoys the classes, and I wish we had a lot of more Krishnas too. Thank you so much, Krishna, being such a wonderful and lovely student. Isn't it? Okay, so that is what they have mentioned. And you know, this energy of heat loss basically comes from the energy stored inside this cell. Inside the cell, what is happening? Some chemical reaction is happening. You connect some wire, some chemical reaction is happening. So basically it should come from chemical energy. So it is the chemical energy of the cell which supplies this power for as long as it can. That's what they have explained. Okay. Now, electrical power they have told blah blah blah. Okay. Then yes, in the connection wires from the power station has a finite resistance. The power dissipated in the connecting wires, which is I squared R. Just to derive the power, the wasted power in connecting wires is inversely proportional to V square. The transmission cables from the power stations are basically hundreds of miles, hence RC is considerable. To reduce this, basically you are going to use large values of V, and that is why you will see that okay, transmission lines are away from the populated areas. Using electricity is not safe. Okay, device called as transformers is used. Okay, now I'll tell you what happens. See, imagine you go to a waterfall. Water falls on a turbine. Water falls on a turbine and it starts rotating the turbine. What kind of energy does the water have? It will have gravitational potential energy. When it falls on the turbine, it basically rotates it, so it will give it rotational kinetic energy. That rotational kinetic energy is then converted into which kind of energy? It is connected to a generator, so it is converted into electrical. It is basically converted into electrical energy. Is that okay, everyone? So if water is continuously falling on a turbine, okay, at a power plant, at a generator, you will see continuously rotational energy is being created and continuously energy has been supplied in electrical form. So that's how you get a power from the generator or from the power stations. It could be thermal power plant, nuclear power plant. This is a hydro power plant. Fair enough? Now imagine this power has to travel a really long distance. It has to travel a really long distance. What will happen because of that? The resistance of such a long wire, because it is directly proportional to the length, will be more, because it has to travel from one city to the other. The power plant is somewhere in some state, your house is somewhere else. So because the length is more, the resistance will be more. Do you guys agree with it? Do you guys agree with it? Now inside this wire, obviously there is some current flowing. So what is the power loss in that particular wire going to be? The power loss in that wire will be current flowing in the wire into resistance of that particular wire. Everybody agrees with this? Into resistance of that particular wire. So if the wire is long, resistance is long, then the power loss will be more. So normal person will think, sir, I will reduce the resistance, I will use a very good material. I'm like, sir, which material do I use? Sir, copper. Even if you use copper for such long distances, the resistance is huge, because we are not talking about 1 or 2 kilometers, couple of hundreds of kilometers. So definitely it will increase the resistance. So can I use silver and gold? If you use silver and gold, people will steal those wires and go off. So you can't use silver and gold, and even if you use silver and gold, still the length is too high to increase the resistance. So you can't do anything with the wire resistance. The only thing you can play around is with this current. So if you reduce this current, since it is being squared, so if the current reduces by half, I square will reduce by 1/4, power will reduce by 1/4. If I reduce the current to 1/10, I squared will reduce to 100th, I will save the power by 100th, guys. So hence the power loss will also decrease. So my aim is always to reduce the current flowing in it. So what they do is there is some kind of a device which we will study later on, which basically is called as a transformer. Autobots assemble, not that transformer. Yes. So that transformer, what it does is it increases the voltage, thereby reducing the current. So because the current reduces, that's why you will see the power reduces. Like, sir, if the voltage is so high, then how will it come to our house? Don't worry. On the other side, there is another transformer which again reduces the voltage and increases the current back to its normal value. Before it is supplied to your house. That's what they do. Whatever they do here, they do the exact reverse before it reaches your house. Now, since this current is very low, but the voltage is high, this is high voltage line. What is this? This is high voltage line. So generally, it is not advisable to stay near a high voltage line. So that's why you do not build any houses, etc. near such lines. That is what they have explained. Okay, that is what they have explained. So blah blah blah, the transmission long distance transfer, but it is, so I'll just mention it over here. To reduce the power loss, these wires carrying current at enormous values of voltage, and this is the reason for the high voltages danger signs on the transmission lines. Okay, as simple as that. So this is what they have explained about power loss and how it can be reduced for long distance transmission. Understood? Very good. Excellent. Now let's move ahead to the next concept of cells and batteries and all these things. Okay, so they have given some concepts over here. So let's understand over here. What is a cell? Cell is basically a device which maintains steady current. A simple device to maintain steady current in a circuit is a cell. It has two electrodes, one is positive and obviously one is negative. So there are some electrolytic reactions which happen and through which you develop a potential difference. The difference of that voltages between the positive and the negative terminal is called as EMF, or the electromotive force. So it is the difference of those voltages on the positive and the negative side. So that is your EMF of the cell. EMF is actually potential difference, very, very important, and not a force. Although the name suggests electromotive force, the unit is not Newton, it is in volts. People earlier thought that batteries give force, but actually batteries do not give force. It is going to give voltage difference. But since the name had already been given, it was too late, so they continued with it. Just like you might have heard, somebody in their childhood was just called Chiku. Now Chiku, that name became so common that the actual name, maybe it was some Rohit, okay, or Sham or Roshan or Rahul. People forgot the original name only. And since we have been calling him Chiku, so we continue calling that person as Chiku. Same way, actually, EMF, the name was given earlier, but people realized it later, but it was too late. So they continued calling it EMF, or else it should have been electromotive voltage. Cool? All right, everyone, till this point. Okay, so this is used because of historical reasons. That's all. Now, EMF is actually potential difference, not a force. See again, what is this NCERT doing? Okay. To understand the significance, consider a resistor. Okay, as explained before, steady current is maintained because of the current which flows clearly across the electrolyte. The same current flows through the electrolyte, whereas P2N, the electrolyte through which blah 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 finite resistance is internal resistance. Okay, this is again an important point. The electrolyte through which the current flows has a finite resistance R, which is called as the internal resistance. where potential difference between P and N, now V is potential difference between P and A, potential difference between A and N, blah blah blah. Thus EMF is the potential difference between the positive and negative electrodes in the open circuit. EMF is the potential difference between the positive and the negative electrodes in an open circuit, that is when no current is flowing through the cell. If however resistance is finite, current is not zero, in that case potential difference between P and N is this. Okay, however, okay, R is finite, is not zero. However, if R is finite, current is not zero, the potential difference is given by V is equal to E minus IR. Okay, fair enough. For practical calculations, internal resistance in the circuit may be neglected when the current is such that it is very small. The EMF is very large and IR is very small. The actual values vary from cell to cell. Internal resistance of dry cell, however, is much higher than the electrolytic cell. Okay, another important line over here. The internal resistance of dry cell, it can come as a statement based question, is more than an electrolytic cell. Okay. Now, let me explain this all to you. Don't worry. We also observe, since the voltage difference is blah 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 from Ohm's law, combining the equations, current is E by R plus R, the maximum current that can be drawn. Okay, this is another important point. The maximum current that can be drawn is for R is equal to 0, and this is basically E by R. Okay, perfect. However, in most of the cells, the maximum allowed current is much lower than this to prevent permanent damage to the cell. Okay, let's understand what this means. Let's understand all these paragraphs, whatever I have written. I have first of all highlighted the important things. Okay, I have first of all highlighted the important things. So the negative electrode develops negative voltage, the positive electrode develops the positive voltage, and all of that. See, when you take a battery like this, this is your positive terminal, this is your negative terminal. For example, the positive terminal developed plus 3 volts, the negative terminal developed minus 4 volts. Then what would be the voltage difference between these two terminals? What would be the voltage difference between these two terminals? Okay, think and tell me. I am very good, Rakshana. Hi Rakshana, thank you so much. Why does it show DNA below? To remind you, if you are not yet a part of DNA batch, be a part of it. DNA students are already active here also and there also and already ahead. So if you are not yet aware of the DNA batch, be a part of it. It's just to make you remind you of that. Okay. So what do you think, guys? What's the voltage difference going to be? Is it 1 volts, minus 1 volt, 7 volts, minus 7 volts? Think about it. I don't think it is minus 1. The voltage difference will be this minus this. So 3 minus minus 4. So it will be basically 7 volts. 7 volts. This voltage difference is basically your EMF of the cell. So the EMF of the cell is basically the positive voltage minus the negative voltage. But if the negative voltage is already written down in the negative sign, so this will become plus. Understand that. Or else you can just think of it as V plus plus V minus modulus. This was 3, this was 4, 3 plus 4 is basically 7. So that becomes your EMF. Is this part understood? Is this much part understood? The voltage difference between the terminals of a cell is basically the EMF. But when do you measure these voltages? When there is no current flowing through this. When out of this, the current should be 0. Nothing should come in, nothing should go out. Such a circuit, when there is no current, it is basically called as a open circuit. What is it called? As an open circuit. It is not closed, it is open. Okay. To represent it, I will just show it like this. A battery with some resistance inside and nothing is connected, it's just open. So then the voltage difference between them will be the EMF. Alright, the voltage difference between them will be the EMF. This is called as a open circuit. Right now, these batteries which are sealed inside, do you think they are open or closed? These batteries which are sealed inside, come on, put it up in the chat box. Is it open circuit or closed circuit? Are they connected by wires to anything back? Is there current flowing? Definitely not. Is it consuming the energy stored inside it? Definitely not. So that's why right now all these batteries are in their open circuit form. Yes. Sukanya, I taught resistance in the previous lecture, part 1. Please check that out. Please check that out. Okay. Great. Now, what is this internal resistance? Basically, inside this battery, when the current flows, inside this battery, when this same current would have flown, you will encounter some resistance because of that chemicals or those electrolytes or that dry powder which is there. So that resistance is basically called as the resistance inside the cell. That is why internal resistance. So through the battery when they go, they encounter a resistance that is shown as internal resistance. You can show it here or here outside the cell, that's okay. I know it is inside, but you can show it outside, there is no harm. But all of this happens inside. There is EMF and there is some loss in that internal resistance. Now, the reason why we told it should be an open circuit to measure the EMF, can you tell me why? The reason is, if current was going, don't you agree there will be some loss in voltage across the resistance? If current was not zero, I squared into R will cause some energy loss, will also cause some voltage loss across this. So this voltage will not give me EMF. Hence, to measure the actual EMF, make sure there is no or negligible current going, then that voltage gives me the EMF. Negligible current means no difference in the voltage across this. That's why I will get the true EMF. Otherwise, it will be different. Now, imagine I use these batteries inside a toy train or inside a torch or inside something. Okay? Do you think the voltage difference across those terminals, which was earlier, let's say 7 volts, will it remain 7 or will it increase or will it decrease? When I'm using this battery in a circuit, it is lighting up a bulb, it is turning on a motor, it is doing something, it is heating something. Do you think this difference, will it still be 7 volts or will it be less than 7 volts or will it be more than 7 volts? Put it up in the chat box. Yes, it will be obviously less than 7 volts. Why will it be less than 7 volts? Because the moment you have this cell and you find that there is some current which is going in it, you will quickly see that this particular voltage difference between them will no longer be E, it will be E minus IR. Why minus IR? Because there is a drop in the voltage. Instead of E, some voltage is basically drop in the potential across the internal resistance. That's the reason for this. So V will be equal to E minus IR. I hope this is absolutely clear for everyone. Everybody with me on this? Clear? One such example for that will be, imagine I take this battery, connect it to a resistance and it is passing through some device. It is passing through some basically device. Usually a device is also called as a load. You are loading the cell means you are connecting it to something. So there is some current. So in such a case, when the current is going in this circuit, if I use Ohm's law, then that current will be that voltage divided by the total resistance. In this case, the voltage is nothing but E. The resistance is R plus R. R plus R is the total resistance. So that would be the current flowing in that particular circuit. And when the current flows, the voltage across the cell terminals will not be E, it will be E minus IR. It will be E minus IR. My day, join in. Even if you are late, it's okay. You can always watch the replay of whatever you have missed. Now just imagine, for that same circuit, what I do, I have that internal resistance, but the load is not there. The load is basically a wire, which means you have shorted the cell. Shorting anything means you are connecting the 2 points with a wire. That is the meaning of shorting. In such a case, what do you think will happen? What do you think will happen? If you again end up measuring the current just like before, this capital R is only not there. So you will see that the current will be E divided by R. E divided by R. But there is a problem. Usually what happens is this resistance is very, very small. Usually this is very, very small, because of which what will happen? The current will become high. Because of which what will happen? When the current is high, it will discharge the cell. It will discharge the cell very fast. It will discharge the cell very fast. So if I take this battery and if I take a wire and just connect it across this, that's it. It's gone within couple of seconds and minutes. It will be discharged because a very large current will flow. Many charges will be supplied. Chemical energy will get utilized very quickly and it will get discharged. That's the reason for it. Is that cool? Everyone understood? That is what they have also explained in these paragraphs, if you notice. So first they talk about how V is E minus IR, and then usually the resistance, if it is small, then you will see very large current will flow. This is that maximum current scenario. This is basically large current or basically maximum current scenario when there is nothing in the way, no load in the way. But that usually should not happen because it can damage the cell. It will discharge the cell really quick. I hope this is clear. So all these three things you should know. Open circuit, this is connected to a load, and finally this is without a load, basically shorting a circuit. These three things they have mentioned over here very clearly. Now usually in NEET exam also and even in NCERT there could be some questions like this, where imagine this is basically your current, this is basically your voltage across the cell, and we know the voltage across the cell V is equal to E minus IR. Now compare this with Y is equal to C plus mx. C plus mx. So clearly you will see who is what. X is your x-axis, which is current. Slope is your R, and constant is basically your E. And your y-axis is nothing but your voltage. This is what it is. So if I use this analogy over here, y-axis is voltage, so this should be a straight line. The y-intercept is positive. The y-intercept is positive, which is E. So this is basically your plus E. The slope is negative R. The slope is negative R. So it should go down like this. It will hit over here. it will hit over here. So it will be a straight line when you draw voltage across current, like this. Voltage across the cell versus the current. If you ask me, what do these points represent? This point is when the x-axis coordinate is 0, that means current is 0. That means it is open circuit. If you ask me, what is this point representing? This is when the y coordinate is 0, that means the voltage is 0. Voltage is 0, that means what? Voltage is 0, that means there is no potential difference across the cell. It has been shorted. It has been shorted. It has been shorted, and that is the reason why you are seeing maximum current. This maximum current was E by R, if you remember correctly. This was shorted. Where is it? Yes, shorted. Yes, E by R. Because there will be no voltage difference here, right? It's a wire. There is no voltage across a wire. That's the reason for it. So this graph is very important. Yeah, clear? Understood how we brought in that analogy, how we compared it with the straight line equation? I hope it is being added in your notes as we speak, or maybe even after the lecture. Shall we move ahead? Everybody clear till this point? Give me a thumbs up quickly or fire in the chat box. Okay. And if you have forgotten to like the video, quickly like the video. If you have forgotten to subscribe to the channel, quickly subscribe to the Vedantu NEET English channel for your Captain Shreyas sir. Okay. Now, they talk about cells in series and cells in parallel. I'll tell you, they have done a lot of nonsense, but at the end of the day, the result is very, very simple to remember. So let's not get into the complexity. Let's remember very straightforward, simple things. So when you have cells in series, meaning one cell is there like this, another cell is there like this, and there could be many such cells with some internal resistance. Let's say this is E1 R1, E2 R2, this is En Rn. I can convert it into one single cell in series and one single resistance in series. Okay, I can convert it into one single cell in series and one single internal resistance in series. So what is that conversion formula? It's very simple. Because the resistors are one after the other in series, this particular Rs becomes just R1 plus R2. Like that, you just add the internal resistance. Whereas for the total EMF, you just add the individual EMF. That's all. So E1 plus E2 like that till EM. Let me give you a simple example for this. Imagine this is 3 volts, this is 2 volts, this is 5 volts, this is 1 ohm, this is 3 ohms, this is 2 ohms. If I convert it into one single cell with internal resistance, what will be those values? Think about it. This value will be, all these cells are in series one after the other. So 3 plus 2 plus 5, which is 5 plus 5, which is 10 volts. This would be 1 plus 3 plus 2, which is basically 6 ohms. Similarly, if there is one battery like this, 3 volts, 2 ohms, then there is another battery like this, 5 volts, and then 1 ohm, and then there is another battery like this of 4 volts, and let's say this is 2 ohms. What would be the equivalent battery and internal resistance? Come on, let's see if you guys can figure this out for the next one. Can you figure it out for the next one? Think carefully and give me the answer. The equivalent EMF and the equivalent internal resistance. What is the answer? Let's see. Come on, my dear students. I want to see who is listening, who is understanding. Hi Tanuja, welcome aboard. Okay. 14. What is it, Sukanya? Resistance is simple, 2, 1 and 2. So it will be just 2 ohms plus 1 plus 2, which is nothing but 5 ohms. But EMF 3 minus 5 plus 4. 3 minus 5 is minus 2 plus 4 is basically 2 volts. So 2 volts is the answer with 5 ohms. Many of you just added 3 plus 5 plus 4. You thought it was 12, but that is not the answer. Be careful, because if you look at it carefully, this battery is in the opposite direction. So you need to be little careful and see how they are connected. If you make a mistake in that, you will get a completely different answer. You might be wondering, sir, you made minus sign here, this battery was opposite. Why did you not make the resistance as -1? Because resistance, no matter whether you connect it like this or like this or like this or like that, doesn't matter. It will be the same resistance. But battery, if you connect it like this or like that, it will go from low to high or high to low. So that is the reason why sign will matter for the cell, but it won't matter for the resistance. That is a catch. Yep, many of you made that mistake. Now I hope you understood and you will not make that mistake in the actual examination. Just like this was cells in series, we also have basically cells in parallel. We also have cells in parallel, meaning this is E1, this is R1, this is En, this is Rn. I convert it into one single cell with one single internal resistance, Okay. In this case, the formula for resistance is very simple actually. It is simply the parallel resistors formula which I have learnt in 12th standard, 1 by R1 plus 1 by R2, and you get basically 1 by Rn, the 10th standard formula, normal formula. The problem is only for the parallel EMF. So EP will be equal to, observe this carefully, you have to write E1 by R1, E2 by R2 like that till En by Rn in the numerator, but in the denominator just 1 by R1, 1 by R2 and till 1 by Rn. That is the only difference. Okay, the only complex formula is for parallel EMF. Otherwise this is simple, even this is simple. Okay, there was nothing different or difficult. So let me show you an example so that you get an idea of it. Imagine you had something like this and you want to convert it into one battery. You want to convert it into basically one single battery with one single EMF, a resistance also. You can clearly see they are in side by side mode, that means they are in parallel. So let's try to find 1 by Rp first. It will be 1 by R1 plus 1 by R2. So LCM is 6. So it will be 3 plus 2, which is 5 by 6. So Rp will be basically 6 by 5 ohms. So we got this. All right. What about EMF? Let's try to do that also. It will be E1 is basically 4, R1 is basically 2, plus E2 is basically 6, R2 is basically 3, upon 1 by R1 plus 1 by R2. That's it. That's the formula. So I have shown you how to apply it. Now this will go 2 times, this will also go 2 times. 2 plus 2 is 4, divided by this is 3 plus 2 divided by 6. So 4 multiplied by 6 divided by 5. So this will be 24 divided by 5 volts. 24 divided by 5 volts. Yeah, correct. Understood? Clear how to do these kind of problems whenever you have to find equivalent EMF either in parallel or in series. Great. So that is what it is. So we are now coming to Kirchhoff's rules after finding equivalent EMF. All right. So let me show you some more examples so that you are, properly getting that confidence. Let me show you one simple example right over here of cells and everything. There is a graph given. This is voltage, this is current, and that graph looks something like this. This is 5 volts. This is, let's say, 20. Sorry, this is basically 0.2 ampere. The question is find the EMF and internal resistance of the cell. This is voltage across the cell. This is the current through the battery. Current through the cell. Come on. Let's see if you guys can figure this bit out. Let's see if you can figure this out. It's not difficult. This graph is something which I had given to you. I'm pretty sure you will be able to do it. EMF and internal resistance. Just remember, just some time back I had shown you this particular graph. Where did I show it to you? Right over here. This graph. Yes. This point is E. This point is I max, which is E by R. And this was related to Y is equal to mx plus C. That's it. So there we go. This is like E minus IR is equal to V. Perfect. So this point is basically the Y intercept, which is basically 5. So EMF is basically 5 volts. That part is done. That part is done. EMF is 5 volt. This point over here, this is basically I max, which is E divided by small r. The maximum current is 0.2. EMF is basically 5. So basically R is 5 divided by 0.2. 0.2 is nothing but 1 by 5 itself. So that means the internal resistance will be 25 ohms. 25 ohms. Understood? Shall we move ahead? Next question. Very good. Excellent. Imagine another example where there is 4 volts, 1 ohm here, and let's say we have something like this, 2 volts, 2 ohms over here, and let's say it is connected to a battery, to a resistor of 2 ohms. The question is, can you find out how much current goes through this particular circuit? What is this value of the current in this particular circuit? When you look at this question, you might get confused, sir. It's a complex circuit, 2 batteries, but don't worry, these 2 batteries are in parallel. So what can I do? I can convert it into a single battery. So the first step for this problem, I will be converting this into a simple circuit. Instead of the 2 batteries, I will write 1 battery. Okay, instead of the 2 batteries in parallel, I will write 1 battery with 1 simple internal resistance, and this will stay as it is. This is 2 ohms. Can I find this? Definitely. Why not? So 1 by Rp will be 1 by R1 plus 1 by R2. So this will be 1 plus 1 by 2, which is 3 by 2. So Rp will be basically 2 by 3. Okay. So this is 2 by 3 ohms. What about this EMF in parallel? E1 by R1 plus E2 by R2. 1 by R1, 1 by R2. 1 by R1, 1 by R2. What is E1? E1 is 4. What is R1? It is basically 1. What is E2? It is basically 2. What is R2? It is basically 2. If you do this, you will get wrong answer. Reason is, check the direction of the cell. So actually speaking, this should be minus. Look at it. This battery is facing this way. This battery is facing this way. So this battery is opposing this battery. So yes, this should be -2. Don't put minus below. So such kind of questions, the minus sign only comes in the numerator, not in the denominator. Is that clear, everyone? Is that clear, everyone? Understood? Pakka? All right. So now you can solve this. So this would be 4 minus 1, which is basically 3. 1 plus 1 by 2 is basically 3 by 2. 3 cancels, 2 goes on the top. So this will become 2 volts. So this is now 2 volts. Now finding the current is a cakewalk. This current will be the voltage divided by the total resistance, which is 2 plus 2 by 3. 2 cancels, so 1 by 1 plus 1 by 3, which is 1 by 1 plus 1 by 3 is 4 by 3. So therefore it will be 3 by 4 amperes. The current is 3 by 4 amperes or 0.75 amperes. Cool. Now you will be able to solve these questions on parallel cells and series cells. It's not that difficult if you see. Okay, I'm showing you examples on how to apply these particular concepts, because oftentimes people go through this theory blobs for by hearting what is this equation. It is so confusing. And you know the worst part, NCERT gave this only for 2 cells, how it will look. But I have given you the formula for even 1000 cells. This will work even for 1000 cells. Okay, infinite number of cells also. Cool. Okay. Now let's come to the next main topic, which is basically Kirchhoff's voltage laws and current laws. See, what happens is many times a circuit may not be series nor parallel. Like, is it possible, sir? It is not series also, not parallel also? Yes, it is possible. I'll show it to you. And in such circuits, you can't simplify it easily. So there has to be some way to solve such problems. So that is why Kirchhoff derived a way, and that is basically Kirchhoff's current law and Kirchhoff's voltage law. And they have basically explained it over here, okay, in a very complex manner. But I'll just highlight the important rules over here. First is called as the junction rule. At any junction, the sum of the currents entering the junction is equal to the one leaving the junction. Okay. And okay. Next is basically the loop rule. The algebraic sum of the changes of the voltage around it in the resistors and the cells is basically 0. This rule is obvious. Wow, very good. Excellent. And then the first example only they give is of a cube. You know, such an example actually came in JEE. And even in JEE, they don't ask such questions immediately, but NCERT had that guts. I mean, literally, hats off to them for giving the first solved example after Kirchhoff's law as the cube problem. They don't even give such questions so easily. So anyways, we'll come to the cube problem, but first let's understand what Kirchhoff's law is. Imagine there is a road like this. I say 2 cars go here. I say 3 cars go in here. Nothing else is happening in this entire situation. After some time, what will happen? These cars are bound to come out. This is all one way. If it goes like this, it can't come back. This is also one way. So they will have to come out in this way. So totally 5 cars will come out of this. Same thing is also applicable even for wires at a junction. This was the junction of a road. Imagine this was 2 amperes. This was 3 amperes. You will 100% see 5 amperes coming out. This is basically called as the Kirchhoff's current law, or basically your junction law or junction law. What is this based on? It is based on the principle of conservation of charges. Conservation of charges. Yes. The total charge has to be conserved. Whatever comes in has to go out. It can't accumulate, nor can it be generated anywhere. If it comes in, it has to go out. That is your Kirchhoff's current law. So in general, I can then say, if I have many branches like this, so many places it will come in, go out, come in, maybe go out, whatever, many things are there. So the total sum of the currents at a junction or basically a node is 0. This is what it is. This is the junction or the node. So whatever you see, the total current at the junction or the node will be 0, or a better way of writing it is the total currents going in will be the total currents coming out. This is usually the more preferred way of writing it. Okay, so that is your Kirchhoff's current law. Is this point absolutely clear, everyone? Yep. So let's see a simple example on this. Let's see a question on this maybe. This is the question. You have to find, if all these currents and directions are given in all these branches, what is the current over here? Okay, let's see who can do it really quick and give me the answer the quickest. You not only have to type fast, but also correctly. Don't make any mistakes while doing this. Come on. Yes, Malati, it will be done next. Moving charges magnetism. Thank you, Krishna, Warrior Pandu. Thank you, VS Vetri. Very good, Atluru. We'll come to his loop rule also. Yep. Let's see how many of you can do this question really quick. Come on. Think. This 5 is going in, 1 is coming out. So naturally the remaining out of it, 5 is coming in, out is 1. So the remaining 4 amperes should go here. It should go here also. Here 2 is going here, 3 is coming out. That means from this more 1 ampere should feed in. So 1 plus 2 will combine as 3. 2 is going out, 3 is going out. So what should come over here will be basically 5 amperes. So 5 amperes should go out here. If 5 is going here, 4 is coming in. So naturally from here, more 1 ampere should go inside this junction. 4 plus 1 will combine as 5 amperes. Next. 1 ampere is going here, 1 ampere is going here. Where will it come from? Obviously this 2 amperes. Okay. So 2 amperes is going here, 4 amperes is going here. Naturally, what is going here is nothing but 6 amperes. So 6 amperes is the answer. Got it, everyone? How to do this question? This kind of question can come in your NEET or even in your board exam. Okay. Very simple application of Kirchhoff's current law. Yes, Madhumati, it is 6 amperes. So that was your Kirchhoff's current law, and they decided to explain it in a very, I don't know, random manner. Now let's go to Kirchhoff's voltage law. Let's go to Kirchhoff's voltage law, which is also called as the loop law. This is based on the principle of conservation of energy, basically. Conservation of energy, basically. Now understand this. Imagine there is some mountain, some river, some valley, some plateau, some city, some mountain, some peak, some waterfall, something is there. So you reach here to the mountain, go down inside the valley, go to the plateau, okay, and then you again go to the mountain, come down, you go on the plains, go to the sea, and you again come back to the same point. Let's say you had some potential energy here, gravitational potential energy. Here the gravitational potential energy increases, decreases, increases, decreases, increases, decreases, increases, decreases, decreases, increases, like that. Finally, what will happen? The total change in your potential energy, what will it be, guys? Won't it be zero? Yep, energy has to be conserved, potential energy will be conserved. You come back to the same place, so you will be at the same gravitational potential energy. Now imagine this was an electrical circuit. In an electrical circuit, is there gravitational potential energy? No, there is electrical energy, electrical potential energy. So if your charge goes around that circuit and comes back, it might increase its voltage, decrease its voltage. Eventually what will happen? The total potential energy change will be zero. That means the total potential drop across a loop will be zero. So that is what it means. So it says that the total voltage drop across a loop when you come back to the same point will be a big fat zero because of conservation of energy. As simple as that. Now, when you are traveling in a circuit, you might encounter a battery. You might even encounter a resistor. So let's say if somebody is going from here to here, somebody is basically traveling from here to here. When that person travels from here to here, he will encounter a voltage change. He's going from positive terminal to the negative terminal, positive terminal to the negative terminal. So is the voltage drop positive or negative? Obviously it is negative. The voltage has dropped, so the voltage change is negative. So when you go from here to here, then the change in the voltage will be minus E. If somebody goes from here to here, it will be minus E. While traveling in the circuit, somebody goes from here to here, you are going from -2 plus low to high. Obviously the voltage change will be plus E. Obviously the voltage change will be plus E. Whereas over here in the resistor, I will need the direction of the current, and current always goes from high potential to the low potential inside a resistor. Which means if somebody decided to go from here to here, against the current, the voltage change will be plus IR, Ohm's law. Voltage is IR, so it will be plus IR. But if somebody decided to go from here to here, it will be minus IR. What will it be? Minus IR. I hope this is absolutely very clear. Everybody with me on this? Excellent. This is the sign convention which you should remember, and I will now explain through example how to use Kirchhoff's voltage law. Observe carefully. Let me take some random third class complex circuit. This is some circuit. Do you see a loop in this? Do you see a loop in this? Let's say this is E1, this is E2, this is E3, this is E4, this is E5, this is R1, let's say this is R2, let's say this is R3, let's say this is R4, let's say this is R5, Let's say this is R6. Let's show some currents also. Maybe the current is like this. Assume the currents. Maybe it is here. Okay. Maybe here it is like this. Maybe here it is like this. Maybe here it is like this. Here actually I don't need the current because there is no resistor. The value is not needed. Maybe here it is like this. Maybe here it is like this. Maybe here it is like this. These are some assumed currents. You can always assume. If it is wrong, if the answer is negative, what will it mean? I have assumed the wrong direction, but magnitude is fine. That's okay. So let's try to apply Kirchhoff's voltage law. Let's start from here. Don't forget, we'll go like this, 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 and come back. Every time I encounter a device, I will either have a positive change or a negative change. But when I add all the voltages, I should get the total sum as 0. So RHS will always be 0. So how will the equation look like? Observe carefully. First, as I go across the battery, from here to here, I am jumping from high, positive, to low, which is negative. So shouldn't it be negative E1? Everybody gets it? E1 will be negative. I am going like this. Now I go through the resistor 1 in the direction of the current. In the direction of the current, the change is negative IR. So shouldn't it be minus I1 R1 minus I1 R1, the next device? Okay. Then I go over here, I encounter the next device, but I am going against the direction of the current. When I go against the direction of the current in the resistor, it is always plus IR. So hence, the next term over here should be plus I2 R2. Plus I2 R2. I reach here, I go across this battery. Negative to positive, low to high. It's a jump. So again, it should be plus E2. Plus E2. I reach here. I see I'm going through this resistor, but I'm going against the direction of the current. So when I go against the direction of the current in a resistor, it is plus. So plus I6 R6. I reach here. I go in this battery. I'm going from positive to negative. High, positive, low, negative. I'm going down. So hence, it should be basically minus E3. I continue. I reach this resistor. I'm going in the direction of the current. And in the direction of the current, it is always a drop. So that's why it should be basically minus I3 R3. I reach here. I reach negative. Go to positive. Negative to positive. It's a jump high. So it will be plus E4. Plus E4. But as I go like this, I'm going against the direction of the current. Against means positive. So plus I4 R4. I reach here. High to low. I'm going down. So again minus E5. I reach here. I go like this. This is in the direction of the current. So it should be a jump down. So minus I5 R5. Minus I5 R5. This whole answer should be a big fat 0. Got it, everyone? This is probably one of the best examples to explain you the signs and how to write Kirchhoff's voltage law. You can't possibly have any confusion after this regarding the signs and the values. Absolutely clear? By the way, can you tell me what will change in this equation? Instead of going like this, somebody goes like this. What will change in the equation? Can somebody tell me? Come on, my dear students, my dear lions. This whole equation, only one thing will change. If I go like this, all the signs will get exchanged. Minus will become plus, plus will become minus. So as an exercise, as an homework for your additional practice, do the same question in the reverse way. You should get the same answer but wherever there is a minus, there will be a plus. Wherever there is a plus, there will be a minus. That's it. That's the only change. So that will clear your doubt. Exactly. Only the signs will change. Very good, Sukanya. Now, let's solve this cube problem. And also then they have given this particular problem before going to Wheatstone Bridge. So what is this cube problem basically? They have told that you have connected a battery of some volts, 10 volts, resistance network which is like a cube. Each resistance being 1 ohm, determine the equivalent resistance of the network and the current along each edge of the cube. Okay. Actually, are you able to visualize this circuit where a battery is supplying current, it enters one corner, it goes in this cube in different paths, finally comes out of this corner which is diagonally opposite, and we have to convert this cube into one single resistor. How do I do it? Okay, let's see. All right. First of all, I feel we should see how the currents will get distributed. And I feel in this particular question, the currents will get distributed in a symmetric way. Why? Because cube is a symmetric figure. So if you carefully think of a cube, you will realize that there is a beautiful line of symmetry like this, or you can think if I go from this diagonal to this diagonal, once I enter from here, I can see that there are 3 different paths like this and like this. 3 different paths which are basically symmetrical. Whether I go like that, like this, or like this, they are symmetrical. Do you see that? Everyone? Same way, if I think of the line of symmetry, if I think of that line of symmetry to be this one, the current enters from here. Can you see it will get divided like this, as well as like this? Symmetry will be involved. So same current will go here, same current will go here, same current will go here. How much current was entering in? Let's say it was I. What will happen is you will see I by 3 and I by 3 current getting distributed. Agree or disagree? Yes, Sridhar will be moving to moving charges and magnetism after that. Equally, 3 parts. If there were 4 branches, 4. I by 4, I by 4, I by 4, I by 4. Okay. Also, with the same logic, at this particular junction, the same current should come out, and it will come from 3 different ways. It's a cube, it's a symmetrical diagram. So naturally, from here, and from here, I by 3, and I by 3 current will come in. 3 I by 3's currents will accumulate here and come out. I'm trying to find the distribution of currents using symmetry of a cube, because that will help me solve the problem. Without currents, I can't apply Kirchhoff's laws, I can't do anything. That's the reason for that. Okay. Now, after going here, can you see there are two equivalent ways? There are two equivalent ways. So one, it can go like this or like this. So I by 3 gets divided into half each. So what is half of I by 3? 1 by 3 into 1 by 2 is 1 by 6. So each one of them will be I by 6 and I by 6. Same thing here. When this current reaches here, there are two paths. So hence, this will be also I by 6. This will be also I by 6. After reaching here, there are two paths. One here, one there. So naturally, you will see this as well as this. Each will be I by 6 and I by 6. That's the distribution of the currents. I have covered each and every side. Now you're like, okay, sir, you did all this, so what nonsense now? What will you do? I'll say I will apply Kirchhoff's voltage law across the loop. You can choose any loop that you want. I will choose a simple loop. I'll go like this maybe. Let's go like this. Simple circuit will go. Let's go like this. Okay, I have highlighted it for you for simplicity. That's all. Now, in this particular loop, let's figure out what are the currents. First, in this cell, I current will go. That same current I will go. Here, how much current will go on this side? This side, I by 3 is there. This side, I by 6 is there, like this. And on this side, again, I by 3 is there. And then again, it comes back to I over here. Please remember, this is actually a resistor. Over here, this is actually a resistor. Even this over here is a resistor. Even this over here is a resistor. Don't forget that each resistance is 1 ohm each. Okay, so I'll just call it as R, R and R for now. R, R and R. Let's apply Kirchhoff's voltage law and see what do we exactly get. Come on. Let's start from here. Starting here, I reach negative, go to positive. So there is a jump. So plus E. So negative to positive, jump. Go like this, nothing here, reach here. Go across the resistor in the current's direction. So I will drop how much? Current, which is I by 3 into resistance. I reach here. After that, I go in the direction of the current. Current is basically I by 6, resistance is R. In the direction, it will be dropping, so negative. I reach here. In the direction of the current, it drops, so it is I by 3 into resistance. There is nothing here, and I come back to that same point, so hence this should be 0. Hence, this should be 0. Take all these gentlemen on the other side. So I'll have IR 1 by 3 plus 1 by 6 plus 1 by 3. LCM of course is 6. LCM of course is 6. So this will be 2 plus 1 plus 2. So what's happening next? So therefore E will be equal to IR 2 plus 1 3, 3 plus 2 is of course 5. So that's what I will get. Now I'll be like, okay sir, fine, you got this. What will you do with this? What will you do with this? Just imagine instead of this complex circuit, what you had was just this battery and just one single resistance, which I call it as the equivalent resistance. How much or how will the current, voltage and resistance be related as? Obviously, it will be related like this. E will be equal to I into R equivalent. E will be equal to I into R equivalent if there was one resistance. So doesn't this equation resemble that? Isn't this resembling this? So that means this entire cube is behaving like 5R by 6. 5R by 6. Got it? Everyone? So hence the equivalent resistance is 5R by 6. Since our original resistance was 1 ohm, so if R is 1, 5 by 6 ohms is the answer. That is what they have done, but in some fancy manner. Where is it? 5 by 6 R. Okay. I hope this is clear. And if you ask me how much current will go, the current will be nothing but substitute this, voltage is known, you will get the current also. That's not difficult. Loved this question. Hi Mahadev. Thank you Diksha ma'am for the blue hearts. Thank you for awakening the kids. Thank you so much. Finally. Yes. Thank you so much Mardel. Thank you Jasmine. Thank you so much guys. So beautiful question about cubes. This has been asked in JEE. If it is asked in NEET, don't be surprised because it is a direct NCERT question. Some of you kids might want to remember this value. I'm perfectly fine with that, no harm. But main thing, what you learn from this question is how to apply Kirchhoff's laws and how in a complex circuit you can solve it without series parallel knowledge. You can solve it to find equivalent resistance. You just had to assume some battery supplying current. You find the distribution, take some loop, write the Kirchhoff's law equation. You see voltage is some current into some resistance. That thing becomes the equivalent. The process of finding equivalent is what you should understand. If you by heart this, I am perfectly fine. But at the same time, understand what we were doing at the background. Okay, we are trying a method for any circuit to find equivalent by connecting this battery, assuming the supplies, distributions, and then voltage is current into resistance. Voltage is current into resistance. That's the main aim. Alright, Warrior Pandus, crystal clear, Alluru, very good Krishna, very good Mahadev plan. Awesome Sukanya, awesome Mahadev, awesome Malati. Perfecto. So where do we go now? Awesome. Here we come. The next NCERT example. Determine the current in each branch of the network. Now, see, over here, many batteries, blah, blah, blah are there. But already, they have shown some distributions. Let's see how this works. So there is a battery, resistor, 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 battery over here. So just assuming few currents right over here like this. Just check this out. Some current I1 they have assumed over here. This current will go here. Some of it will go here. Some of it goes here. How much will go here? Think about it. If some of it goes here, how much will go here? The remaining. I1 has come in. I2 is going out. So naturally this will be I1 minus I2. Which law did you use here? Subconsciously. Kirchhoff's current law. Currents coming in, currents going out must be the same. Currents coming in, currents going out must be obviously the same. Okay. Now, after reaching here, okay, they have assumed some current in this particular branch, which they call it as I3. See, I1 minus I2 enters here. I1 minus I2 enters here. I3 goes out. So what should happen over here? Okay, if they assume this to be like this. If they assume this to be like this. If I assume this to be X, X enters in, I1 minus I2 also enters in, collectively it becomes I3. So therefore, X will become how much? I3 minus I1 plus I2. So I minus I1 is there, I2 plus I3 is also there. I2 plus I3 minus I1. So that is exactly what they have written down over here. Till this point, everything clear? How these values they have got? This was I2 plus I3 minus I1. Okay. Then over here, what they have done, whatever current goes here will obviously also go over here. So this is I3. This is I2. I3 and I2 together, what will that become? That will just become I2 plus I3. Both of them together, Kirchhoff's current law, it will become I2 plus I3. So once this is done, you can apply Kirchhoff's voltage law multiple times to solve the problem. But in the NEET exam, you will never get such a complex question because it is very time consuming. But I will just show this to you, how Kirchhoff's law can be applied. You can choose any loop that you want. Okay, for example, they have chosen some loop ADCA, I think, ADCA, okay. So I'll just show you how it works, and then we'll choose any random loop and see how it works. A, D, C, A. This loop, if you choose, starting from here, how will the Kirchhoff's law equation look like? Starting from here, going in the direction of the current, it will obviously drop the voltage. So minus I1 minus I2 into resistance, which is 4. Reach here, going against the current, so it should be an increase. Current into resistance. So I2 plus I3 minus I1 into the resistance, which is 2. Reach here, go in the direction of the current, so negative IR. So I1 into 1 is equal to 0. That's how you write Kirchhoff's voltage equation. Clear, everyone? You can choose even more loops if you want. You can choose even more loops. Say for example, somebody chooses this particular loop. Okay, you start from here, go like this, and come back over here. How will that Kirchhoff law equation look like? Kirchhoff's voltage law. Start from here, go like this. I encounter a battery, negative to positive, so I'm jumping by 5 volts. Negative to positive, low to high, it's a jump up. Reach here, go in the direction of the current, that means there is a drop. Current into resistance. So I2 plus I3 into 2. In the direction of the resistance, drop, so minus. Current is this one. So I2 plus I3 minus I1. Resistance is basically 2. This is equal to 0. Got it, guys, how to apply Kirchhoff's law? If you understand how to write it, that's it. Yeah. So they have just written down the equations and solved it, and you get the answers. That is not the point over here. Main thing is, are you able to apply Kirchhoff's law or not? So even let's see if you can write it down for some another equation, another loop. Maybe you go like this. Maybe you go like this, starting from point A. So if you start from point A and apply Kirchhoff's voltage law, I'm going in the direction of the current. So negative I2 into resistance. In the direction of the current, negative. So this current into resistance. So I2 plus I3 into 2. In the direction of the current, so again negative, and that is basically I1 into R1. And there is a battery over here, negative to positive. So negative to positive, so plus 10 is equal to 0. Okay, plus 10 is equal to 0. I hope this is clear. I think I missed that 10 over here by mistake. My bad. So I think while going like this, I missed that 10 over here. So my bad. So plus 10 was also there. I just saw that over here. So plus 10. Yep. Great. Done. Sorted. Cool, guys. Everyone? Yeah. So this is how you write Kirchhoff's law equation. Okay. So now we are coming to the last part of this, which is basically the Wheatstone's bridge. Is an application of Kirchhoff's law as shown in the circuit. And they say if you have resistors, etc., then that is called as a Wheatstone's bridge. There is a galvanometer, and in the case of a balanced bridge, in general, there will be currents flowing across all the resistors as well as the current through the galvanometer. The special case, this is very important, special interest is the case of balanced bridge. When the resistors are such that the current through the galvanometer is 0, such is called as the balanced condition. Balanced condition. So all of this they tell, and we obtain the balance condition to be this is called as the balance condition, where the galvanometer will give 0 or null deflection in the circuit. Wheatstone's bridge will provide a practical method to determine unknown resistance. Yes, determination of unknown resistance. This is basically called as a meter bridge. Okay, and then they give that particular example over here. Okay, let's understand what this is. Listen to me carefully. Imagine there is a resistor here, there is a resistor here, like this, and then there is a resistor here, and there is a resistor here, like this. Say for example, some current entered over here, okay, it got divided into two branches like this. So if for example at this point the voltage was 20 volts, after reaching here the voltage became, let's say, 12 volts, then maybe it became over here back to 0 volts. Maybe while passing here the current became, let's say, 10 volts, and here it became 0 volts again, obviously. Now tell me, if by chance I connect some device which deflects if current passes through it. Galvanometer is such a device where you pass the current, it gets deflected. If I connect a galvanometer, will it deflect or not deflect in this scenario? Tell me that. Thank you, Divya. I'm so glad, and I really hope all the students in the country, especially learning in English medium, find this channel. That's the reason why I ask you to like, share, not just physically through, on your WhatsApp, but also talk about this in your school, amongst your friends, amongst your relatives. What do you think? Will it show any deflection or not? Well, there is clearly a voltage difference which is there. So definitely current will flow from high to low voltage. So current will flow and this current won't be zero. So there will be deflection. There will be deflection in that galvanometer. This setup of those resistors is called as a Wheatstone. Wheatstone is the name of the person. It's not like, sir, there was a stone made of wheat and he made a bridge. Somebody told me this and I hit my head. Imagine some teacher had told one student, and that student came and asked me, sir, there was really a bridge, sir. That bridge was made of stones, and that stone was made of wheat. Then I realized teacher was not at fault. The teacher was joking. The student did not understand the joke. Because the student had asked, why is it called Wheatstone Bridge? So teacher funnily said, stones were made of wheat and then they made the bridge, and then it was unbalanced. So the bridge fell down. Like London Bridge is falling down. Okay. So this is unbalanced because there is deflection. Versus a scenario where you have these resistors like this. Again, let's say this is 20 volts, maybe this is 15 volts, maybe this is 15 volts, this is 0 volts. Somebody now decides to connect a device which deflects when passing current. There is no voltage difference, so clearly the current through this will be 0. So there is null means 0, null or no deflection. Such a condition for that Wheatstone is said to be balanced. So this is called as a balanced Wheatstone bridge. This is called as the balanced Wheatstone bridge. Exactly. Very true, Sukanya. Such a student is intelligent, sir. That's how I understand whether the student is smart or no. When I crack a joke, if the student laughs, then I understand the student is intelligent, smart, will do well. Student doesn't laugh, I only get tense. Why student didn't laugh? He didn't understand my joke only. I was joking to him. Okay. And this balanced Wheatstone bridge happens if this is R1, this is R2, this is R3, this is R4. This by this and this by this are equal. When R1 by R2 is R3 by R4. That's when it is balanced. If it is not equal, it will be unbalanced. This is the balancing condition. Is this absolutely clear, my dear warriors? Yep. By the way, you know what? This is even valid for even more resistors like this. Even more branches can be there, guys. This is 1 ohm, 2 ohms, 3 ohms, 2 ohms, 4 ohms, 6 ohms, 2 ohms, 4 ohms, 0.5 ohms, 1 ohm, 1.5 ohms, 10 ohms, 20 ohms, 30 ohms. Oops. Some crazy circuit. Somebody was really jobless while making this circuit. Imagine in this circuit, they ask you to simplify. You'll be like, sir, what is this? But let me tell you, this is actually simple. Yes, this is actually simple. You know what? This is a Wheatstone bridge, but this is multi-layer, multiple Wheatstone bridge are there, or extended Wheatstone bridge. If you see, there are how many branches? 1, 2, 3, 4. Each branch has 3 resistors. These resistors are in the ratio 1:2:3. This is 1 time, this is 2 times, this is 3 times of this. 0.5 into 2, 0.5 into 3. 10 into 2, 10 into 3. 1:2:3 ratio. So the ratio is same. Ratio is same. That's it. All these yellow resistors are useless because it is a balanced bridge. So useless because there will be no current in the circuit. So you can just forget them. So this is the equivalent circuit. Just to draw it without that. Now these are in series. These are in series. This is in series. This is in series. And they are in parallel. So now you got it, guys. How the circuit is actually a simple circuit. Everyone, so this is an extended Wheatstone bridge which is still valid. The ratio of the resistors in all the branches must be the same, then it works. 1:2:3. Okay. So there is a question. Oh, by the way, before going there, now they tell that listen, you can use Wheatstone in some way to find an unknown resistance. Kind of makes sense actually. Imagine this is like when I show a resistor with an arrow mark, what does it mean? What does it mean when I show a resistor with an arrow mark? It's a vector quantity, is it? No. It means I can change the resistance. So this is like a fixed resistance, but this means it's a variable resistance. This X happens to be an unknown resistance. This happens to be a variable resistance. These are like fixed. These are like some fixed resistances. So what happens is you basically vary this resistance till there is no deflection here. When there is no deflection, basically balanced condition, what will happen is that R by X will be R1 by R2, rather X will be R into R2 by R1. You know R2, you know R1, this R you changed till you adjust and see there is no deflection. That's it. You can find the unknown resistance. So this Wheatstone is used to find an unknown resistance using some fixed known resistance as standard resistances. Got it, my dear students, how this works? Okay, that is what they have mentioned in the last few things. Determination of unknown resistance, that setup is called as the meter bridge setup. Okay, so there are 4 arms of a Wheatstone bridge as follows. Oh, by the way, some of you will be like, sir, these experiments which are there, no sir, please can you teach me that? How many of you know the magic? How many of you know the magic? The magical words. Experimental physics. Let me type it. Ooh, what is this? Wow, experimental physics. It was the first time somebody did it on YouTube, especially on the English channel. Click on this. It's one single class, complete physics, all experiments explained one by one. It's the same me. I might look a little younger. Yeah, the age difference between me then and now might be around 90 to 95 years, not much. Okay, so I hope you won't find it too old. So just go through this, all experiments, guys. All experiments are there right over here. Every single thing explained in detail. So check this out. Okay, some of you do not know this. That's why I had to show this to you. Okay, cool. So what is this? AB is 100, BC is 10, CD is 60, DA is DA. Why DA? CD is basically 5, DA is 60. The 4 arms are shown. Galvanometer of 15 ohm resistance is connected across. This calculate the current through the galvanometer when a potential difference of 10 volts is maintained. And then they start doing all this and they find the current. Now, you might be wondering, sir, why did they do this? Isn't this balanced? Shouldn't the answer be 0? Just check it out. What is the ratio? 100. This is 100 divided by 10, R1 by R2. This is 60 divided by 5. This is basically 10:1. This is basically 12:1. So they are not equal. So hence it is unbalanced circuit. Oh my God, you'll be like, sir, unbalanced, sir, what to do now? Meter bridge. Shreya, please check that experimental physics class. Okay, you will find it there. Now, whether it is deleted or not, we'll have to see. Wait and watch for the syllabus to be officially released. So, till that time, okay, just assume that only that basic concept is there as per NCERT, but otherwise, it is not there. We don't know. It might come, it might not come. We have to wait for the official brochure to come. So till that time, no comments. Okay. Some people will make videos on guessing. This is there, that is there. NTA declared 2 exams are there. NTA declared 5 exams are there. NTA is doing this. Some people, news articles, rumor, they say that it is official NTA news. I don't know how people see that videos, forget people saying how teachers can make such videos. I never understood that. It's really shameful for such teachers to make such videos. So make sure that you are not stupid enough to fall for such, clickbaits. Okay. So in such a scenario, my dear students, what you should remember is that current will flow. So you have no other choice but to use Kirchhoff's current law and Kirchhoff's voltage law. No other way. Okay. Atiluru, the scholarship test syllabus I have already mentioned over here. How to prepare for MVSAT strategy revealed. In this particular video, right, I have given the complete syllabus for all the grades, 11th, 12th, everything. So check this video out. I given the pattern, everything, the syllabus, everything. So just check it out. Okay, this video is there in the live tab of our channel only. Preparation strategy. So for solving this question, you assume the distribution of currents. There is no other way. to solve this particular question. Like say for example, current I will pass over here. This will get distributed as I1 and maybe I2, okay? And once this I1 reaches here, some current will go through the galvanometer. So if I1 is reaching here, Ig is going here. So the remaining will be I1 minus Ig. I1 went here, Ig went here. So remaining will be I1 minus Ig. And this Ig will come here. This I2 will come here, will add up to become I2 plus Ig. Finally, they will all add up to become I back again, and it will go through this battery. You just have to choose some loops and solve the question. You can choose any loops. Say for example, I choose this particular loop, or I choose this particular loop. Choose these loops and solve using Kirchhoff's voltage law. So if I apply Kirchhoff's voltage law over here, say starting from this point, I encounter a battery, so plus E, which is basically plus 10. Across the resistor in the direction of the current, so minus I into resistance, which is basically 60. Current into resistance, so in the direction of the current I am going, so minus I2 plus Ig into 5. Back to the same point, so this should be 0. So this is one equation. This is one equation. Similarly, you can write an equation for this also using Kirchhoff's voltage law again. So let's say you start from here. In the direction of the current, it is a drop, so I into resistance. In the direction of the current, it's a drop, so minus Ig into 15. Opposite, it's always a rise, so plus I2 into basically 60. That is equal to 0. So make equations, solve them. That's what they have done. If you notice, they have exactly done this. They have written an equation, another equation, another equation. Solve this to get the answer. Is that clear? So that was the method to do it. No other way, no shortcut, nothing else. Cool. This is how you solve unbalanced Wheatstone's problem.